Okay, and welcome everyone to the second session on the first day of the OpenVSP Workshop 2020. For those of you joining us live for the first time this session, please remember to increase your viewer quality using the little gear icon and bump that up to 1080p. That'll give you a nice clear image, and that's going to let you follow along with these tutorials using the best image available. So we're going to go ahead and let Rob continue on with his fit model demonstration, and either he or I will give a demonstration of how that works within VSP, and we'll continue on with the sessions according to the schedule on the main page. So Rob, you're welcome to take away whenever you're ready.
All right, thank you very much, Brandon. I'm Rob McDonald, and this talk will be about fit model, which is a technique for reconstructing a 3D model in OpenVSP interactively. And this has some interesting use cases. What we're looking for here is ways to interoperate with other 3D models and in CAD. And you can think about this as sort of being a circle. I'm not really suggesting that you would cycle a single model through the circle multiple times, but there are tools that exist to do basically every step of this loop. For example, you can go from VSP in a VSP model, and you can generate a surface mesh, or you can export IGES and step files, which you can then take into CAD or into a grid generation tool and generate a surface mesh from those. And once you have the surface mesh or any sort of laser scan or point cloud or other representation, you can bring that into fit model, which is this assisted parameterization, which you can use to generate a VSP model. So again, I wouldn't suggest that you really do this on just VSP models for fun, but for example, you might have a legacy model from someone else in your company, or an old product of yours that you say you want to look at re-winging an airplane. You could bring that existing model of that airplane into VSP, do an assisted parameterization, a fit model to it, and now you have the baseline, and now you can use VSP to do a parametric study for that re-winging that you're looking at. So there's lots of other use cases. Maybe you have an old wind tunnel model that you've done a laser scan on, or you're looking to reverse engineer a propeller or something. So there's different reasons why you'd want to be able to do fit model. Again, some of these reasons are laser scanning to reverse engineer a part, you're interoperating with CAD or a surface mesh that somebody else already has. You want to do a derivative of an aircraft, re-wing it, stretch it, adapt it to a current mission. You want to build a baseline for a design study. So you have a CAD model as a baseline. You want to use that then parametrically in VSP. And in particular here, what you're going after in this is you don't want a dumb fit. We're not looking for a shape that just happens to match in a 3D sense. What we're trying to do is we're trying to match the intent of a VSP user. So let's just say that there's different ways you can build VSP models. For example, you can position a component in XYZ space and it's there, or you can position a component by attaching it to a parent and using relative motion and attachment to position it in the same place. When you use attachment, you've put some design intent in that model so that later on when you move things or change things, it moves the way you want. Whereas if you just placed everything in 3D space, when you go later change the model, you have to update all of these other positions. Your tail won't stay at the tail, your tail surfaces won't stay at the end of the fuselage. You'll have to move them every time you make your fuselage longer. So the goal here is to allow the user to build the fit model in the way that they want, in the way you build a normal VSP model. First, I need to lay some ground rules and talk about some nomenclature for fit model. As we said earlier today, every component, like this pod, has surface parametric components, surface parametric coordinates. In this case, the U direction goes from nose to tail along the pod, and the W direction goes around the circumference of it. So we have these surface coordinates that we need to know about. If you've done a laser scan, you have some point in a cloud. There's going to be some point P, and there's many of them. So we've labeled it PI. So there's many of these points in the cloud. And what we're doing is we're associating every point in the cloud with a point on the surface. And so there's the cloud point and then what we call the target point, which we're going to call T. And so these match. There's an association PI to TI, and we draw that line between them to show that association. And the goal here is to change the shape so that TI coincides with PI, right? We're going to try and move this and change the shape to make them match. And we do this as a least squares fit. And so we have a minimization problem where we want to minimize f, our functional, which is a vector, which is a function of x, which is a vector. There's many variables we're varying to minimize f. F, as it turns out, is the sum over all of our points. If our points are labeled with L, there's m of them. So there's m points that we're looking at, and they each have a parent and a target, a point cloud and a target point. We're taking the distance between those, p minus t, to get the distance between them, and we're squaring that because it's a least squares formulation. And we have to sum. There's three components, x, y, z. So k is the x, y, z index. So we have all of these things. And so we have m times 3 terms that end up in this squared sum. The target points are what's moving. So the target points are really the function of x. The point cloud doesn't change. So that's why t is a function of x. And our x vector is the combination of our design variables, v, that we choose, as well as whatever u-free and w-free parameters are. And I'll explain that a little bit more. A target point, there's different kinds of target points. This target point, in general, will be free to move about the surface. It could scoot up here in U and scoot around in W, and it can freely move around anywhere on the surface it wants to. And so that's a target point where U and W are free, and those UW are actually controlled by the optimization problem. The optimizer gets to choose where on the surface T is to help minimize that least squares problem. Sometimes we don't want to do that. Sometimes we know, hey, this point in my cloud is the nose point of something. That's the leading edge point. That's the nose point. And so I want to associate it with a T point that I've forced to be at U equals 0. And so instead I'll put U fixed and I'll fix W. So I'll lock those down at U0, W0, fixed. And that way that T point can't move. It can't scoot around anymore. So we'll have a fixed point, and then we also have free points. And so the design variables in the optimization problem are the shape variables that we give it freedom to change, and the UW free points that can scoot around. And this is important because what you're really doing when you work with fit model is you are crafting this optimization problem. You pose the problem, you pose the optimization problem, you pick the points, you pick the targets, you say whether they're free, and you pick the variables, and then you hit go, and the optimizer solves that optimization problem. And we're doing that interactively. Now, as it turns out, this kind of optimization is best solved using what's called a Levenberg-Marquardt algorithm, which is implemented. We use the C++ Minpack library to do that. And it's a really good solver for Levenberg-Marquardt. And that LM optimization, instead of actually summing all of these things for them, all these 3 times m things that we're going to minimize the least squares, we actually give it all these terms individually, this little lowercase f. So lowercase f is our point cloud minus our target point. So we give it to it individually as this long vector, which is 3m long. And then we also, so it works on the derivative, this Jacobian of all those f's, the derivative of those with respect to all of our vectors, well, all of our design variables. And recall that x, that's our shape variables as well as u free and w free. So what we're doing here is we're the user, and what we're going to do is we go through and we identify what are the relationship, the pairing between the points in the point cloud that we want and the target points that we want to match. Every target point, we identify it as either fixed or free in UW, and if they're fixed, then we lock down that value. We identify the parameters we want to change. What are the design parms that we want to change, which will be our V, and then we control the optimizer. We tell it go, and this is the workflow where the user gets to choose these things as they want, and it's set up this way. It goes back to getting a model that was built the way you would have built it, not the way just some algorithm does it for you. So think of this as more as like a wizard that helps you through the process than just a one-click, it happens. There's a lot of GUIs to fit model through the different tabs. And as with all of the tabs in VSP, typically the most important tab is to the left. And as you go to the right, you'll use the tabs less and less commonly. To start with, you've got to pick the points and associate the target points with the cloud points. And so there's buttons up here at the top to work with a cloud of points. You can select one, select a box, select none, invert the selection, hide them, show them, all those kinds of things. It'll always tell you how many points are selected up here at the top. Once you've selected points, you say add to target point, and it will add whatever points are selected to become target points, and they get associated with whichever geometry you want. So you choose the geometry, the component here. They get added as either fixed free or fixed fix, and you can dial in those values. So you set these to be free or fixed, and you set the values when you add them. You can also delete or clear all of them. This little window here will tell you how many target points there are, but how many you've added. Okay. The next tab is to pick the variables, and you can choose these design variables, whatever you're going to use. You can either use this pull down setup at the top, and we'll demo that when we do the demo, by either choosing the container, which is going to be which component, the group, and the parm, and then you can add, delete, and clear. You can also just drag and drop. You can go to that parameter, and we'll show you this, but it's going to be the easier way to do it. You just drag and drop it anywhere in this big blue box, and it'll get added to your variable list. Here's a list of those, and again, you can add, delete, and clear all those variables. You can also work with the variables through the variable tree, and this is similar to other ways, but instead of the pull-down menus, you can explode a tree and look at all of the variables in a model, and then you just click with the checkboxes which ones you want included in your problem. You can also do drag and drop selection here. So it's entirely redundant with pickvars. It's just a different way. Sometimes if you're doing a bunch of similar variables, it's easiest to come into the tree where you can just come down and run down the list. Oh, I want X, Y, Z location and Y, Z rotation, and you can very quickly get all of those. This fit model tab, what it does is all of the variables that we've selected, you get a slider. So if you just want to manually come in here and make sure it's the parameter you want it to be, or manually adjust one of them, this just consolidates all of the parameters, all the parameters you've picked in either the variable tree or the pickvars. It just gives you a way that you can edit them here. So that's just a quick little way of editing those. And then finally, the last tab is the save or import tab. And what this is doing is it's actually saving that optimization problem. So it's saving the set of target points, the association, the UW fixed, and the variables that you've used, that you've chosen. It's saving that formulation of that optimization problem. And the reason you might do this is you might, say, set up a really complicated thing to work on skinning a part of the nose, and then you want to save that optimization formulation and then go do something else. Say you want to work on the tail or the tip or some other part of the fuselage, but then you might need to come back and revisit part of what you were doing. And so being able to save that optimization problem gives you a way to store that work that you've put into stowing that problem. When you import one back in, I've got it marked here as additive. And what that means is if your current optimization problem is, say, matching the nose, and you import something you saved, which was matching the tail of a fuselage, you import it, you'll now have the combined optimization problem where you're trying to match both the nose and the tail. So that's a pretty neat thing that you can use in some clever ways. Again, this is a more advanced part of fit model. Once you need it, you'll understand how you'd use it and it'll make more sense. At the bottom of all of these, there's the actual control of the optimizer. That's the go button. You hit fit and that's the go button. But there's other things going on here. First, the number of degrees of freedom in your current optimization problem are reported, as well as the conditions. So think of this as number of equations and number of unknowns that you're trying to match. Likewise, there's two, you can adjust the UW of the target free points. On the left, there's the search button, which does a global optimization to minimize the distance, but only changing the UW free. On the right, there's a local optimization. So it's just going to take and it's just going to do a Newton's method from the current starting point to try and improve the UW. I'll demonstrate why you'd use these. Update distance just recalculates the metric, which is what's output here. And fit does the actual full optimization problem. Here's an example, and this is what we'll run through in a minute live. You start where we've got a bunch of points around here in a cloud, and they've all been associated with a pod. And so, again, we have our cloud point, we have our target point, and the default pod doesn't match it very well, and you'll see our distance metric is 2.5. So we set it up, and we do our first step of optimization, and you'll see that it matches a lot better, but still not very well. We got down to about a 0.45 sum squared distance. What you'll notice is some of these lines are really long and others are really tight. What's happened here is this point was associated with another point over here, and when it moved, it got trapped in a local minimum. And so this point is associated now with a point that's not in the optimal place, and it got trapped in a local minimum. So what you need to do is you need to do that global optimization to instead update that target point for this cloud point. And when you do that global optimization, you'll see that that point moves much closer. So I'm going to toggle back and forth between these two. Notice which lines are changing. And what's happening is those are all updating to better points. So we're getting, all these points are getting out of local minima, and they're moving to a new global minimum as a better starting point. And once we've improved that, then we can do another round of the overall optimization. And in doing that, we fully recover our original shape. So that's just an example, and we'll demo that in just a minute. I'm going to show some screen grabs of some other cases that I've done. For example, here's a case where there's an AGARD report that includes a body shape for a wind tunnel test that is meant for CFD validation. And they specify the points, nose to tail, along the shape. And so if you want to take those points, which are specified in a text file in this AGARD report, you can pull them in, and then you can fit model to recover that shape as exactly as you want it. It's a long story, but someone I know had a CAD model that they made off of Burt Rutan's drawings for the Boomerang airplane. And they were kind enough to share an STL file with me of that. And so I was able to pull in that STL file, get the point cloud from it, and by going through, I was able to build a VSP model that matches that aircraft. And we've got some close-up pictures. Here it is without the points, just to show what the VSP model looks like. Here's, say, one of the nacelles. Again, here's just the cloud of points with the VSP model matching, and then just the VSP model alone. So there's another use case matching a legacy model. The Drela at MIT, the D8 configuration that NASA did some wind tunnel testing with before, they had a very, very fine resolution CFD mesh that I was able to pull in and then make this VSP model to match. And likewise, the X57 is based on a Tecnam P2006 fuselage. I was able to take the STL file from that CAD file from Tecnam and use that to build the fuselage model that is in the Tecnam models that you can download from the hangar. This was an interesting case where the STL file came in multiple components. There was one file for the tail, one for the very end of the fuselage, one for the aft fuselage, one for the nose, one for this midsection. And each of these, to be honest, they didn't necessarily line up very well. There were sometimes gaps, there was sometimes overlap. The STL files were a mess. And so one thing that I did in VSP was I took, for example, this mess of a fuselage, and I used the planar slice capability to then slice that fuselage and create nice uniform ordered slices on the right. As well, you'll notice that the resolution here is not very uniform. There's some areas where it's very sparse, where you might want more points. There's areas where it's too dense and you might want fewer points. And so by slicing it, I was able to get a more uniform point distribution and get them where I wanted them. So using slicing is a great thing to do if you have an STL or a connected surface mesh rather than just a loose cloud of points. And for that, I am going to turn it over to Brandon. If Brandon, you don't mind doing a demo of how to make this work, that would be fabulous.
Not a problem at all, Rob. I'll go ahead and back out of full screen mode.
You're muted, Brandon.
Am I? Oh, no, I'm not muted on the stream. I'm muted on the Teams meeting. So now everything should be good to go. I'm going to move this off, and I'm going to go ahead and open up VSP on this side. So let me double check what's going on here. Okay, so everybody here online, we're going to give Rob a bit of a break until about 2:30 when we start the next presentation. And we're going to do almost the same example that he showed using a pod. So the first thing we're going to do is add a pod to our model, and let's give it a few more, say 21 and 21. Give it a little bit of a finer surface, and let's come in and change not only the length and the fineness ratio, so let's make it a length of about 5 and a fineness ratio of 5. Why not? So we have this shape here. And again, if the demonstration here is coming out a little fuzzy on your viewer, make sure that your quality is on 1080p and that little gear icon. I'm going to switch to a hidden view so that we can see all these points. And another thing that I'm going to do is I'm going to go ahead and move this to the right slightly, and I'm going to pitch it up a little bit. So it's not in a typical set, and it's also been moved and rotated a little bit. So we can't just drop something in and make it fit automatically. Now the way that you can take a VSP part and get yourself a mesh, you can go in and let's just do something like comp geom. We're going to get a mesh. Okay, that's all well and good. Now you notice if I click on this mesh geometry, we can come over here to other and convert it to a point cloud. So I'm just going to click on that, and now we have all these points. So now I'm going to delete that mesh, and we can pretend that what I did was import this mesh. So this is what we'll start with, and we're going to delete this original geometry. So now it's as if we started off from scratch with a cloud of points, and OpenVSP has no idea how to get there just by hand. So if we add another pod, here we've got the default. That's all well and good. We say that that looks pretty smooth. Why don't we go ahead and give this maybe just 11 and 11, because we don't want to make it too easy. Now we could just go ahead and go into fit model, and notice how all these turn green, and as I'm moving my cursor around, we have these little points highlighting. I can either turn on to select one at a time, where if I were to say pick what I suspect to be the nose, okay, if I click somewhere else, it's going to deselect that point. So we've got that one. If I turn that off, I can select multiple points. Or if we want, we can just select region, and I can grab all of them. But for right now, let's go ahead and select none. And the way to do this is to build up and match it incrementally instead of trying to just brute force the routine. So if we go to select one and say that we want to match the nose, and we know that we want it on the nose of this part. So rather than allowing it to do free, what we're going to do is we're going to fix it to the 0 and 0 UW positions. Now, what should happen is when I add target, we get a line from that point to that point. So now that's our target, and it's only 1. So if we go to the variables, we can say, well, all right, let's start off by moving it. So we'll give it, say, some Y location, and it looks right, but what if we give it X, Y, and Z? So you can see down here we have 3 degrees of freedom and 3 conditions. That's a sound problem to solve, so what we should be able to do is click Fit. And notice how it snapped everything over. It pulled out that Y location, and we have a 0 distance metric. Okay, great. So if we come back to pick points, what we can do is clear this out. We can do a select none. We can clear the targets. We can go to variables, and we can clear all variables. So now we're basically starting off with a brand new problem. So now, if we say that we want to start matching up where the tail happens to be, again, we can kind of see that this is the tail. We can click on this one, and if we know exactly where we want this to go, say the tail of this component, we can set it again to fix, but in this case we want U to 1. So if we now add target, you can see that it's got that attached, and we're going from the tail to the tail. So now this is going to be a slightly different problem to solve, because we want to adjust the length and we want to adjust the rotation to make these fit. So what we're going to do is come into our pod, and we're going to give it length, and we're going to give it some rotation information. So if we give it some rotation in Y and Z, or X and Y rather, let's go ahead. We've got 3 and 3. What would happen if we click Z rotation? Now we have 4 degrees of freedom and 3 conditions. That's not necessarily going to work. So let's pick one and say that it's probably not rotated about its own axis, and we are going to delete that variable. So now we can click Fit, and what it did was, again, it rotated it around and figured out where that tail needed to go. So now that we have those two, really the only thing that needs to change is to now give it the fineness ratio and try and recover that shape. So again, if we clear our variables, we're going to clear all our targets, we're back to square one. And so we could pick any surface on here that we like, but why don't we go ahead and just pick a handful of them and see what we can do. So instead of select one, Rob or Justin, I think we've got a live mic and it's coming through on the Teams.
Hey, I'm back.
Okay. So what we're going to do is turn off select one. We're going to pick a handful of points as we go around here, and we can pick whichever that we like, maybe give a few up here at the nose and some of these others. And instead of fixed, we're going to let these be free. So we are going to add those targets, and it connects everywhere along this body. That's all well and good. And what we're going to do is now give it fineness ratio. So if we click Fit, you can see that even though we have a different tessellation setting in the radial direction, or in the W direction and in the U direction, what it did is it almost perfectly matched everything. It's down to a 0 distance metric, and we have that original pod shape. So as you're all aware, we're up to 2:30, and we're going to get ready to move into Rob's presentation. But that was just a demonstration on how you can take a step-by-step approach to make fit model function much more efficiently than to just throw hundreds of points at it and brute force it into submission. So Rob, if you have rested your voice and are ready to go, I'm happy to go ahead and close this out. We can answer some questions about this online, but we'll go ahead and have you do your presentation.
All right. Thanks a lot, Brandon. Thanks, everyone, for sticking with us. I hope you're enjoying the workshop so far. If you are just joining us, we're going to give you a reminder. Hit the gear down in the corner of your video stream to make sure that you've set it to HD. YouTube defaults to low D, and so you won't be able to see lots of the screens and see much resolution if you don't change that to HD. This next talk is about parameter linking and advanced parameter linking, as well as user parms. And we'll go through and talk about why you do this and then how to do it. So linking, why would you want to link? And we'll talk about what linking is as well. But linking allows you to establish some relationship between disparate parameters. And doing this allows you to change the parameters of a model, essentially. You can build your designer intent into it so that you build what you want your model to be like into it. And through that, you reduce the design space dimensionality. So instead of, when you're making a change, having to update 5 variables, you may only have to update 1. And through this, you can even go so far as to introduce new parameters and new physics and some physics into your model. And used appropriately, all of these things can be really powerful to allow you to build very expressive models with as few parameters as possible. That's important because in general, you always want to use the smallest number of parameters when you're doing some sort of a design or an optimization study, just because it makes everything a lot more intuitive and faster. So first off, there's user parms. There are, I think, 15 predefined user parms. Frankly, these aren't that useful because they don't have great names, user 0 to user 15. Instead, what I'd really recommend you do is come over to the Create tab if you want to make user parms, and this allows you to come in and name the parameters yourself. You can give it a name. They'll always be in these certain groups, but then you can give it a minimum and a maximum of value. And so you can create parameters like disk loading, gross weight, number of disks, disk area, disk spacing, something like that for a VTOL model. And whatever kinds of parameters you want. And then again, through linking, you'll be able to use these to drive your model and determine other things. So in general, go ahead and create a named user parm when you need them. The last tab on user parms is the adjust. And so here, any of your created user parms that you made, you get the ability to come in here, and this is where they get a slider. So you can come in, you can adjust their values by sliding them around right here. Linking, and we're starting with simple linking, allows you to create a linear relationship between any 2 single parms. And this relationship is right up here in the title bar. So parameter B is equal to parameter A times the scale plus an offset. So you've got a linear relationship between 2 single parms. And then in the GUI, you'll notice we have parameter A here on the left and parameter B on the right. So these are pull-down menus to choose what the parm is. You can set what that scale and offset values are, and if you want to use the scale and the offset, you can even limit the extent that you'll allow it to go. And you set all this up to set up a link, and then you say add link. And that link gets then displayed down here. And you'll see that in this case, they've linked where a pod's length is the driving parameter that then determines its fineness ratio. So B is a function of A in this case. And so you've linked the length to the fineness ratio of a pod. It's a little silly, but it illustrates the point. So this is simple linking that's been around a long time. A little bit more recently added is what we call advanced linking. And the way that that works is you get to pick any VSP parms you want as input parms, and those will have their own identifier that VSP uses. So first we map them to an input variable. You give them labels. Instead of wing aspect ratio, which is a very long name, you map it and you might just call it AR to give it a simple name that you're going to use in code. So first there's a mapping between the parms to the variable names you want. Then there's the code. What do you actually want to be done, to be calculated? And then there's the output variables, where you have output variables as again, named quantities in code that then get mapped to the VSP parms. And so this is sort of the process for advanced linking. And to do advanced linking, you're specifying this mapping on the input and the output side, as well as what code happens. The advanced linking GUI First, you can have different advanced links. So you name them. So there's the add, delete all, and name box up here at the top to create them. Then there's an area for picking the parms. So you can use the pull down menus to choose the parm and give it a name. So when you want to create a mapping, that mapping for an input parm, you'd put in a name here in the var name. So for example, for disk loading, you'd call it DL. So you type in DL here, and then you'd browse to the disk loading, which happens to be a user parm, and you'd say add input var. As an alternative, you can type in DL here and then drag and drop that parameter to this input parm box. And I'll demonstrate that. Hopefully we'll have time for a live demo. But the drag and drop is a really great way. But you give it a name, and if you drag and drop it into the output parm, then it creates an output mapping. And if you drag and drop it to the input, then it creates an input mapping. But this shows your mappings. And again, you can delete and delete all on your input and your output mappings. So that's what this part of the GUI does. And then down here is where you put in the code. So this is, you just type in your code using these variables that you've specified, and you do your calculations. Here we do a calculation of the disk area. We calculate the diameter of the disk. We have the number of them that are going to be output. So here we do a spacing calculation to determine the Y values of that, where we have our end disk there, and then we determine the angles. So this was something to go out and calculate some disk spacing in a model. This code is in AngelScript syntax. AngelScript is the built-in scripting language for VSP. And so if you want to access our API natively, you'll do so with the built-in scripting using AngelScript. Or if you want to write a user-defined component, you'll write that component in AngelScript. In both cases, AngelScript is really just a very simple scripting language that is intended to be embedded in C++, and it's intended to be really easily used with C++. So that's why we chose it. In the particulars, though, what you're doing with advanced links is it basically looks like C. And to be even more simple, it basically looks like math with semicolons at the end of each line. And for most things people will do it as advanced linking. You don't need to be a C programmer. You don't need to be a C++ programmer. You don't need to be an AngelScript programmer. You just need to be able to do math with semicolons at the end of the lines. In particular, what is supported is, in terms of math, is you've got all your trig functions, your log, your power, your square root, things like that. You do have exponentiation with a double star, modulus with a percent sign, add, subtract, multiply, divide, and basically anything you want to do math with semicolons. Don't do something stupid. This is AngelScript code. It is actually much more general. So you could write a while loop and put your model into an infinite loop in an advanced link. And you can imagine what's going to happen if you put an infinite loop into your own model. So in general, you don't need to do looping, right? Don't solve the Navier-Stokes equations in an advanced link. Don't do anything crazy. Keep it for simple things, and you'll be fine. And with that, I'll go and do a quick demo of some of these things. If there are any questions, feel free to ask them on the fly as we're going along here. I will try and address them as we go. So to start, I'll replicate that first example. Here's a pod, and just a default pod, and we'll start under model. First, we had the design variables, not design variables, we're in user parms, the user parms menu. And as you'll see, we have the 15 built-in user parms, and then the ability to create them. And we can come in here and we can create foo, and we create that. Now foo is a parm, and we can create bar and create that as a parm, and we can create all these parms that we want. And then we come to the adjust, and we can adjust their values over here. And right now they don't do anything, but we'll maybe come back to those parameters in a little bit. Next, under model, we talked about simple linking. So that's just the link tab, and that pulls up. And as we said, this allows us to create a linear relationship where B is equal to A times a scale plus an offset. So we've moved this around from when the screenshot was done in the presentation, so that now A is on the left and it shows up on the left and B is on the right, so that's nice. But as an example, we can come here and say we want to do what we did there. So we'll start by choosing the container that's going to be the pod. We're going to choose a design, and we want to do the length. And so the length will be the driver, and we want to link that to the design to the fineness ratio. So we've chosen those two parms. And what VSP is going to do as you're setting this up is it's going to calculate right now what it thinks you want to do. So right now, it's just going to do that with no scale, but with an offset of 5, because that would create that same relationship. It calculates here an idea for the scale, so that if you instead wanted to scale them and not offset them, if you just flip those, now it would, again, create the same relationship. Minimum surprise principle here. It's going to, when you create this link, it's not going to change the model. But what we're doing here is now we're going to say that B, which is our fineness ratio, is 1.5 times the length. And so if we say add link, we've created that link. And you'll notice that the fineness ratio is now red and the length is green. And green means that it participates as an input to a link, and red means it's an output of a link. It's determined by a link. And so if we change the length, because that's the green one, as we change the length, notice the fineness ratio is updating. And in fact, because of the relationship of this, we're actually maintaining a constant diameter. So we've linked these parameters, and we have that linear relationship. Now, other neat things you can do is if you click on the length button, it pulls up some information about that parm. It gives you its name, its group, its description, its min, its max, its current value. But also, if you click links, it shows what links it participates in. So here, it's a driving link on some, it's a driven link by others, for both advanced and regular links. So there's information about that if you just click on the head of it. The other thing that you can do is if we delete this link and we want to recreate it real fast, instead of choosing through these pull downs, because that's a little bit laborious, what we can do is we can actually drag and drop. And this time, let's do the opposite. Let's have B drive A. So here we can drag and drop from this button for the fineness ratio, and we drag and drop onto that, and boom, it sets us right up. And likewise, we can drag and drop the length here, and it sets that length. And so a lot less effort. We just we drag and drop those in. We've got a scale. In this case, it's 1 over what it was before to get the, again, minimum surprise, the same effect. We say add link. And now everything's reversed. Green and red are reversed. But now the fineness ratio is driving and the length is driven. So that's an example there. Let's go ahead and delete this link just to simplify. That's pretty much everything on regular links. We can also go into advanced linking. And here, what we're going to do is start by creating our first link. So there we go. There's our first link. And we're going to do something similar where first we need to create the var name. So here we're going to want the length to be len. And as I said, we can come through here and we can choose pod, design, length, and we can say add an input variable. And then we're going to have FR for fineness ratio. But instead of going through the pull downs, I can just grab fineness ratio and drop it on the output box, and it'll create it with that name. So now we have two mappings. Remember, we said we had to have a mapping of the parameter to a code name. So we have inputs of len and outputs of FR. And so here we can just say FR, since it's an output, is equal to, well, to be simple, we can say, 0.5 times len. Math with a semicolon, put a semicolon at the end. Then you hit the compile button. It's red right now, just showing that it has not been compiled. We hit the compile button. It not only compiles it, if it's successful, it'll go gray, but it then applies it for the first time. And once again, our red and green relationships up here show us that we've linked something. And so now if we change length, we see that our fineness ratio updates. Of course, we can do more complicated things. For example, what if we wanted to do that the fineness ratio is 1/2 times the sine of the length? This will be probably terrible, but it should be hilarious at the same time. Since this is C, that means that it's going to interpret my length as a length in radians. So let's compile it, and let's see what this does for our fineness ratio as we change our length in radians. Well, that's kind of boring because I can't really tell that things are highly nonlinear. But you get the idea here. We could do something like maybe the log to do something more complicated. So here we'll change, and we should see that, oh, see, it goes really fast there at the end, and then more slowly as we get bigger because there's a log relationship. So you can see that nonlinear a little bit there. And of course, you can do multiple lines and you can have multiple outputs. So advanced links allow you to have multiple inputs and multiple outputs. They also allow multiple lines of code. And I'd like you to think about these not only in terms of geometric relationships, but also think about them in terms of the physics you can implement. The example shown earlier showed making disk loading an input parameter as a user-defined parameter, and then having gross weight. And so now you have disk loading as an input, and the gross weight of the vehicle as an input, and it'll automatically calculate then the diameter of your disks so that you always have models that match the intended disk loading. I'd say you can go much further and do more complicated things. For example, you can build a model where the tail area is driven by a tail volume coefficient calculation. And the tail position is at the end of the fuselage, and you can enforce that through attachment. And so then when you go and you change the length of the fuselage and you have a fixed tail volume coefficient, it will automatically shrink or grow the tail to match the desired tail volume coefficient. Another example might be that if you are designing UAVs that communicate through a satellite dish, then you might have a set of algebraic equations that relate the diameter of your satellite dish to the bandwidth and the gains and other parameters about your antenna. And so now you can have an antenna that automatically gets sized based on the bandwidth requirement for that vehicle. And you could even go so far as to put in the relationships about your sensor, how many megapixels and how many frames per second, and or even all the way to pixels on target and a nearest calculation as to can you identify the target. And so then you can have something like, if you need to be able to identify a video target from a 12-mile slant range in infrared, and you're going on KU band satellite, you could have links set up to size both the optics of your sensor as well as the size of the dish, all based on what's your slant range and what's your requirement for your sensor. So you can move parameters from being purely geometric to include the physics or the payload or whatever's driving your design. And that can be a really cool, powerful thing for your VSP model. And I think that's really all I had planned as a demo. I'm happy to take any questions about parameter linking as we go.
Yeah, Rob, there was a question that was asking if we can put intermediate variables within the advanced parameter link. So I think that's mostly, say you compute something and you say that A is some calculation and then you use that variable later. I said that we absolutely could, but I don't know if we need to demo that. I think that answers the question, but it's totally up to you.
And you can, and the thing is, you just have to treat it kind of like C. So if it's a double or an int, whatever it is, you say double, as you said, A is equal to, say, len over 2, and then here fineness ratio is equal to A times length. So now we're going to get a squared relationship here, but we can compile that, and now as we change length, we're getting a, there's the fineness ratio is turns out the square of the length divided by 2. So that's that's a case where you can introduce intermediate variables. Absolutely.
Yeah, we just had another one pop up here that asks, is there any reason to implement a number of simple links versus equivalent of advanced links? Do simple linear links run faster than the advanced links?
So there's some gotchas. There's some difficult things about linking. First, advanced links, you might invest a bunch of time in setting one of these up. And so you'll notice there's file write and file read as options over here. And these only write and read exactly what your code is. So if you've written some incredibly beautiful code that does exactly what you want, you might want to file write and save that off for posterity in case you want to reuse it in another model or you need to read it back in. So that's the first thing, is you can save this for later. The next thing that happens, and this is a bit unfortunate, and we probably ought to make this more friendly about VSP, but this link only exists and only works as long as these parameters exist. So let's say that we have a model that's a little more complicated. It's got a wing and a pod. And here we've got our first link, and we can make our second link. And we're gonna, sorry, I just renamed that one. There's first link, let's add one. This is our second link. And on the second link, what I'm gonna do is I'm gonna have span as of this section as an input, and then we're gonna have sweep as an output, which is kind of a crazy thing to do. And we're just gonna say sweep equals span. And so now we have this model where if I change the span, it changes the sweep. Okay, so that's kind of weird, but that's what I wanted to do. So we have two links. One is pod only, one is pod and wing. And I'm going to go ahead and add another one, and I'll say this is third link. And here I'm going to say that the input is the area, and I'm going to take the wing area here. Let's use the record. No, we can change the area. Why not? We'll change this to an area. So now it's a driving parameter. So now we have area as an input, and I'm going to make the X location of the pod is the output. And so we'll just say that X equals area and compile that. So now the X location is now over there at 50. And as we come to the wing, again, as the area changes, the pod moves, right? It translates. So the point here is that we now have three links. One is using only parameters of the pod, one is using only parameters of the wing, and the other has both wing and pod. When these update, it's going to go through and update these in order. And so if there are any loops, if you have loops in your advanced links, it will try and resolve those. If they go in order, it will try and resolve them. Generally, for the most part, you're going to want to avoid situations like that because it just creates counterintuitive behavior. The gotcha I wanted to address is, what do you think happens if I delete the pod and the pod no longer exists? And I'll demonstrate it in a minute, but what's going to happen is any of these advanced links that involve the pod, unfortunately, this is not very user-friendly, are going to get deleted. They're going to get blown away. And so remember, we had a pod only, a wing only, and a wing and a pod. So if we come up here and we just delete the pod, it's going to blow away. Those two, the pod only and the wing and the pod links, got blown away. And the only link that survived was the one that's the wing only. So because of this, you're going to want to most likely not put links into your model until you've really established the baseline model. You've got the architecture added. You've added all the components you're going to add. You've set the exec types You've chosen the airfoil types. You've chosen rounded rectangle or super ellipse or whatever you're going to use for your cross sections. You've chosen those. You've set up your model. You know how many cross sections you're going to have. You've got those things pretty well established. And once you have those pretty well established, then is when you're going to want to go in and start adding your linking, because then parameters aren't coming and going. They aren't, and you're much less likely to lose work through the advanced links. So I don't know if that answers the question, but it's a bunch more information that's hopefully useful.
All right, thanks a lot, Rob. We've got just a few minutes here before our 3 o'clock talk, so we're going to take a quick break and get up, walk around a little bit, and then we'll come back at 3 o'clock for a presentation on CAD and CFD interaction and some advanced modeling techniques. So hope everybody joins us for that here in just a minute. Okay, it's 3 o'clock. We're going to go ahead and roll into the next presentation, which is to work between VSP, CAD, and CFD interaction and some advanced modeling techniques. So this presentation can be a little bit of a hodgepodge depending on how you look at it, but it's going to show some of the techniques that work between going in between VSP and CAD systems and CFD tools, and how some of that workflow can go. And if you don't happen to have access to one of these tools, say a nice CAD package, there are things that you can do in VSP to approximate some of the features that you can get out of a CAD system. So we're going to work with some introduction, move into tool interaction and VSP model setup and techniques. and then how to get into some CAD model detailing and adjustment, and then grid generation and refinement. So basically we're going from an OpenVSP model into a high-fidelity CFD solution, and we're starting off with the VSP geometry as the source so that everything that we do lines up and works well. So the main reason for this is that the boundaries between parametric modeling, CAD, and CFD are blurring, and they have been for years as computer power increases and we get some more information ahead of time. So advanced knowledge of the aerodynamic or structural or manufacturing issues early in the process saves you time and money later. And streamlining this process between your various tools saves even more time and effort, and it also helps avoid miscommunication between your various teams. So this presentation is intended to just convey techniques and some lessons learned, it's just from using a variety of design and analysis tools. It's not a comprehensive list. If you have something that works well for you, by all means do that. This is just to put it out there so that if you need it for a reference, you can have it. So the idea here is that we're starting from a parametric model. We add some details in CAD, and then we get things out and we generate grids for things like CFD solvers. So the idea here is that there's this iterative design change among all these different tools to where one is good for one thing and another performs another task very well. So each of these processes is integrated and each tool is used to their individual strengths. So if something is really good at adding detailed features, do it in that tool and then hand it off to the other ones and vice versa. You don't want to try and necessarily brute force things in VSP if you don't have to. Trust me, it's a big headache. So let's start off with some stuff in OpenVSP, namely your surface resolution. So if you're using a grid as a reference surface for things like, say, a solver setup, you want the grids that you build in your grid system to be able to project and grow onto this reference surface. So you want it to be as close to a true representation as you can. So give it a very high tessellation value and you'll get a good grid onto a good surface, instead of trying to map, say, a really great, well-spaced grid onto a surface that has a bunch of sharp corners to it, because the grid system will do that, and it's going to give you crap information out. So if you're using the VSP surface itself as the solver model, just make sure and set your tessellation and grouping according to your needs. So increase tessellation and group points where you expect large gradients. So for example, if you're running a wing in isolation and you want to get a better capture of the downwash out at the wingtip, just make your tip grouping a little bit better so that you get more points and you can get that to capture some more of the behaviors. When you're exporting for things like 3D printing, use really, really high tessellation and you're going to get a much better surface for your source, and then your slicer can do whatever it wants to with that. So sometimes you need to beware using airfoil files with excessively clustered points, and this can tend to happen for things like the leading edge. If you have more than about 100 to 200 airfoil points and they are highly, highly clustered down at the leading edge, for example, it can cause a little bit of surface ringing where all those points are smashed together, and it can either make it wiggle when you go out to something like CAD, or if you try and use that as a reference surface, it can do some interpolation that can cause problems. So your best bet is to use between about 100 and 200 foil points, and that's usually good enough. So in my experience, when you try and set things up for gridding, you can go ahead and do some of the work ahead of time in OpenVSP so that you don't have to go back and do as much interpretation in your grid system or your grid tools. So you try and have a maximum growth ratio of about 1.1, maybe 1.2, depending on the fidelity. And for your wing settings, 201 points all the way around in the chordwise direction, and maybe 80 or 100 in the spanwise, depending on the wing. And your leading edge, trailing edge clustering for high fidelity methods, set them to about 0.1, and you'll have a nice surface to where you can start growing your grids. If you're doing a body type, set the number W to 361, so you get about 1 degree per section. That's going to give you a really nice surface for your grids. And the thing is that VSP has come a long way, and when you're exporting to grids, you want to make sure that the model is in the solver units. So if your VSP model is in meters or in feet or in inches, make sure that when you dump everything out, go ahead and just save yourself the trouble and scale it to whatever the solver wants. So you don't want to give your grid setup model in inches and then have to go into each individual one of those and scale them down, when you can just as easily do it in VSP. So if you're going out to CAD file via IGES or STEP, these processes have improved a great deal, particularly over the last year. So they're basically unit agnostic. Whatever you tell it is when you export, be it feet or inches, it will set that, and then it's going to come into your CAD system. But make sure that your tolerances are set up so that you can do a good surface import. So this is just a layout of some of the file formats that you can use among the various tools. And so now we're going to try and cover a few advanced VSP techniques. So say, for example, you don't have access to a really nice CAD package, but you still want to model some of these features to do some basic either panel method or a free CFD tool like you can get from NASA or elsewhere. So we're going to cover some of these, and I do kind of go quickly through some of these examples, and I apologize if we kind of breeze by something. There's a lot to cover in this, and it's mostly just to give you an example of what you can do. So in this case, we had a wingtip nacelle that we wanted to put a fillet and fill this area in. And I'll try and highlight that here with this laser pointer. That originally we started with just a 2 cross-section piece that we tried to blend in and achieve the desired shape. And as a first approximation, it may be okay, but it's not quite there because it's really difficult to match a 2D section to a 3D surface, and you're not quite getting things the way that you want them. So you can see here that there is a little bit of a fillet built in here, but it's not quite right. But if we do the same thing to something that's essentially symmetric along a plane, you can get some pretty good behavior. So in this case, we did basically the same thing and used some cross sections that were aligned with the wing leading edge and then this pylon and the nacelle. And you can get a pretty darn good strake just from doing this with a few cross sections. This was really easy to do. And if we click, we can see that these surfaces trim themselves nicely. They'd have nice intersection points where you can either intersect with VSP or you can intersect in your gridding tool and get these out, mesh them in, and you're good to go. So we're almost there for something like this, and it's pretty useful. But what we realized was that gridding in CAD software doesn't care whatsoever about what surface is really normal in OpenVSP. So you can use the inside of a component as the blending surface. So as this video kind of rotates around, and hopefully it's coming through nicely to the viewers here online, you can see this region is the surface that's coming out as the fillet between the wing and this tip nacelle. And by using a fuselage part, it allows us to have lots of fine control of the cross-section shape and size and placement and orientation. And we can take it even a step further by using the skinning parameters to try and make that intersection between the wing and the tip nacelle be as smooth as we can so that we can try and control where this actually hits. This is very, very, very tedious. So you have to manually place all of these. If you wanted to, technically you could go through and script it by using a surface intersection and calculating where everything needed to be. I certainly haven't done that yet, and if that's something that you want to do, you are more than welcome. But we did the same thing for that pylon nacelle junction, and by making them symmetric about either side and controlling some of the cross-section placement and skinning, we could very finely create some strakes that fit this kind of 3-to-1 ratio where you wanted them to be nice and deep. They have a nice growth. This is all based on NACA wind tunnel studies back in the day. But we're again using the inside of this surface as our reference that we grow onto when we have our grids, and we just build those up in our gridding tools. So this all ended up working really, really well. But the point here is that if you're going to do this, make sure that there are well-defined intersection curves in between either component. And that's going to make things much easier for either your CAD or your gridding tools to pull out those intersection curves that you can use for reference. So in this case, you can dump these things out and use them as step or IGES files, and then you can build them up from the CAD. So the actual physical part that's built for manufacturing is based on the stuff that came out of VSP. You use those intersection lines as a guide and then build things up in a way that makes sense for the manufacturer. So in this case, here is this wingtip nacelle and wing with that fillet that we built up. This is the overlay of the various grids that we were able to build and grow onto this surface. And when we do that, you can see that rather than have this weird discontinuous jump in the boundary layer between the gradient as it's coming back along the nacelle and the gradient as it's coming back along the wing, the fillet does exactly what it's supposed to do, and it allows those two to talk to each other and to smooth along. So we actually got much better behavior as we were coming back this direction by putting this arbitrary VSP generated fillet in here. Now for higher fidelity, if we really want to know what the best answer is going to come out of CFD is going to be, of course we can slice up the CAD file and get what it actually is. But for a first approximation, this worked really, really well. So a bit of a summary on this is that the VSP components can absolutely be used to blend between parts in a model. Just use them intelligently and understand that there are going to be some inherent limitations to what you're trying to do. So it's not going to necessarily do a full curve-to-curve mapped constant radius transition between two bodies unless you put in a lot of work. But if you're doing things like blending between parallel slices or a wing to wing or a wing to a body, you can get something like, say, a glove and bat blend between a wing and a transport fuselage pretty darn easily. And, blending these components can be directly imported to either your CAD or your grid software. So another neat thing is that existing designs from CAD can be approximated in VSP by importing the STL and using either a by hand or fit model. So Rob demonstrated that you can use fit model to make some really complex, interesting shapes just by taking some time and getting it to fit. So what we'll talk about now is using OpenVSP components to remove material from CAD parts. And a lot of these, you'll notice I'm using these high lift propeller blades from X57 because that's what I'm most familiar with. That's what I was doing at the time. So the demonstrations that you're going to see are part of the design process and go into how I kind of created these things. So in this case, the cutter parts are these in gold, and the actual physical blades are in red. And the gold part is used to clear material away from the nacelle to make sure that the red propeller blades aren't going to strike the nacelle when they fold back. So using a transparent view, you can see these parts of the nacelle back here that are going to get trimmed out. And these are the solid cutter blades. And the nice thing is you can export these parts separately, and then you only use a single cutter to save yourself some time. So you cut it once and then make an axial pattern in CAD, and it gives you exactly what would happen if you tried to dump out all 5 of these. So here is the CAD part after I cut those pieces away. And the things that you need to watch out for are to avoid sharp corners and multi-directional bends, because that's going to make things really tricky for your grid tools. So if you can go in and manipulate things and maybe fix them a little bit in CAD to avoid those sharp corners, your grid tools are going to be much, much happier and can build volume grids much easier than if you leave these high curvature regions, which we'll show later. But in this case, all of those blades that came straight from VSP nestled perfectly in these little cutout regions because that's what they were designed to do. And if we zoom in a little bit, you can see that those cutter parts left a 10,000th of an inch constant distance from the lower surface of this blade here where they touch, and back here it maintained a 30 thou clearance. So not only are these things able to clear material away, but they're able to do so very, very accurately. So moving off of that and to talk a little bit about hinges, if you know that you're going from OpenVSP and you're going to need a physical hinge later in your CAD model, it's really easy to dump out a small pin cylinder to use as a reference in CAD. So all you have to do is attach a VSP cylinder to the rotation center and extend it along that axis. And when you write out the step file, you've got a little cylindrical reference that you can say, hey, here's my pin. This is where your mechanism connection goes. And it makes it so much faster than having to do the math and align everything. And the neat thing is that hinges, or even a combination of hinges, can provide a more realistic control of your component kinematics than simply mixing a bunch of blanks together. So hinge parameters like rotate and translate can all be linked together to define something like a pin or a cylinder or a slide and various types of joints. So in this case, this is an example of a 6-level jointed hinge, all driven by a single fraction. So you can see here in the top right that I'm moving a user parameter that I created, and what that does is it commands each of these hinges to deploy by either a percentage of its 0 or 100% deployment angle. So I can make this thing wrap up on itself or fully deploy, kind of like maybe a soft robotic arm. So it can wrap up on itself, it can extend, and you can set these to be whatever joint angle you want it to be. And you can set this up using user parameters and links to be, say, stowed or deployed. So you can imagine something like this being exceptionally useful for putting together, say, a complex landing gear mechanism. So we're about halfway through this particular talk, and we're doing okay on the number of slides. So with this, I'm going to give a bit of a word on scripting. And the reason that scripting is so powerful, particularly with something like a propeller blade, is that you can rapidly alter configurations by changing a few parameters and inputs, and it drastically reduces the time involved compared to modifying things by hand. And it's really important if you need repeatable and accurate models to be created. So rather than going through and trusting that you got everything right and didn't fudge the numbers when you were typing it in, it does it for you. So an example case here is again the conformal blades and cutters. Each of these propeller blades were defined by between 40 and 80 radial cross sections. That's all of those blade curves, and that depended on how many inputs came out from the X-rotor model. And what you'll see is that trying to manually change these, VSP has a lot to update. It's got a lot of work to do, and it takes some time. But by scripting it, it's orders of magnitude faster. So in this case, we've got a single section modify example where what I'm trying to do here is thicken the trailing edge and the leading edge to make this cutter component. So it's already set my offsets to make it a cutter. What I need to do is thicken it so it's going to clear the material away. And as I'm doing this, you can see how long it takes to only change a single parameter here. And there's one. So it's going to go through the same process for the leading edge. We have to go and tell it that I want to turn something on, and then it's going to allow me, and then I have to set the value, and it's got to update. So you have to do this for each individual cross-section along the blade, and it takes a lot of time. But instead of that, this is what happens when it's scripted. So I run a script that does all of these modifications for me automatically. And what you're going to see here is that I run the script, it's going to think about it, and it does take a little while to run because it's still a complex part. It has to update everything, and it does have to build it. But not only does it run the entire blade in about half the time it took to do one cross-section, it pieces them up and it's good to go and it's all accurate. So that saved me tons and tons and tons of time. So that's just a brief demonstration on how useful and powerful scripting can be. Another really useful feature that we have are VSP trimmed surfaces. So this is basically like a trimmed CAD export and piecing everything together. What it's going to do is it's going to calculate the intersection curves and the intersection surfaces for you. And they can come out as plot 3D. You can dump everything out in IGES or STEP. And it's kind of similar to a tool called AGARD to Surf that I used with Chimera Grid tools that we'll talk about later. But don't neglect that this feature is here, because some of the intersections and things that you would tend to rely on either CAD or your grid tools to accomplish can actually be done in VSP ahead of time, and they're ready to go, so you can start off with that work already done. So a brief word on how to fix things in CAD while we're talking about it. An IGES file or a step file might not come into your CAD program as a solid because maybe there's some misaligned edges, maybe there was a tolerance issue, but it might come in as a surface. And the easiest way to come in and fix this stuff is to look at your wireframe view, and typically a CAD system is going to identify any gaps or misaligned edges by highlighting them. Now, most of these CAD tools have a way to go in and heal these back up, and once that's done, you can solidify. And the reason that we tend to work in solid components is because you can use those to either merge or cut, you can use them to build in rounds, you can use them as a basis for another piece of geometry. So in this case, if we start off with, say, a parameterized and simple VSP geometry like we have here with one of the X57 nacelles, we bring that in as surfaces to CAD, and then we thicken it up and we add some features, and we end up with the final manufactured part. But the important thing here is that we started with a VSP geometry. And once we got to the part where we had our detailed design, once you're past the parametric side of the design stage, you can take whatever changes you make in CAD and feed them back into VSP. So it's not just one direction. You can sync them back and forth so that your VSP model starts following your CAD instead of the other direction. So things that you should watch out for if you're coming out of CAD into your grid tools are pinched regions and high curvature areas. And you can do that by doing a surface analysis just to see where they are. And this is going to help with your exports. So to kind of get towards the close of this talk, for the grid system that I did for these high lift propeller blades and the nacelles, I used a feature of Chimera Grid Tools called AGARDs to surf, and it's part of the open source MIT AGARDs library, and it's part of this design system with Engineering Sketchpad. So I was able to import CAD and then add that to things that I already had in place from OpenVSP. And the nice thing is it gives you all of the edges that it calculates, it gives you the surfaces as rectilinear grids, and then from there you can start to build things up and grow. And the final result is a combination of all these various sources. So we've got a nacelle and a spinner and a nose cap, and all these nacelle grids come straight from VSP. The blades, because they didn't need to be modified at all, also came straight from VSP, and the source was the source. But all these little pockets where I had to do this detailed work came from CAD, and because I used the same source, all of these lined up, all of them meshed perfectly in my grid system. I didn't have to go back and do any taping. They just worked. And they integrate seamlessly. And that's the point. It saves you so much time and headache by going in and making this work off the bat. So thank you all very much. I understand that that was quite a lot of information. We've got a few minutes to spare before the next talk, so I'm more than happy to try and answer any questions about that. But for now, I'm going to go ahead and close out of the presentation, and we'll get ready for our next presenter.
Hey Brandon,
Yes, sir.
if no questions come up, there's some questions that have come up online that I could do some demos. So let's give people just a moment to ask any questions to Brandon, and then I'll try and address some of the other questions that have been coming up.
Let's see.
Okay, so I think, let me go ahead and grab the screen, and I'll try and do a little bit more complicated demo of fit model. Somebody was asking about, they had a complicated cross section and they wanted to try and match it. So let me just off the top of my head see if I can figure out what I'm going to do is I'm going to come in here with a fuselage, and give me just a second, everybody, to just sort of doctor this up. But let's change one of these to a rounded rectangle and change that radius a little bit there so that we have something intermediate. And let's make it tall and wide and skewed and keystone. So we'll make it some weird shape. And then what I'm going to do next is I'm going to come into CFD mesh. We'll talk about this another time, but we're going to hit mesh and export real quick. And I did that because I'm using this to create a cloud of points. So we'll say this is my point cloud. And right now what I'm going to do is close that and not show there. But what I want to do is, oops, not insert. I want to import the STL file. So there should be an unnamed STL. So this is, I just imported this cloud of points, right? So this could have come from your laser scan or from a legacy model or wherever it came from. But you can see this is that cloud of points from that shape. And in fact, what I want to do there's different ways I could go, but what I'm going to try and do for the user is demonstrate how you would use this to match a given cross section. They wanted to match something intermediate here, and so there's a couple of ways. It is connected. We'll come back to that in a moment, but you'll notice under the mesh geom, if you click on this thing, the other tab, there's an option to convert it to a point cloud. So if we do that and we convert to a point cloud, and then if we show only the point cloud, you'll see this is the kind of input you would get from a laser scan, just a bunch of disconnected points. And I'm going to assume that we want to match one section intermediate here. And so just for fun, to give you an idea of what I'm thinking about, we're going to add a stack. We'll shade it right now, but I'm actually going to go to the end of the stack, and we're going to delete the first couple of cross sections, and we'll go to the beginning, and we should be able to cut it down to, okay, we're down to the minimum number. We'll make this one a circle and just open it up a little. So here we have a stack that's just 2 cross sections, and I want to match it to somewhere down here, somewhere down the body. So we're gonna match the we'll say we're gonna match it at 12. We're gonna try and match whatever this section is here at 12. And so there's a lot going on. The first thing is you've got a point cloud. There's just too many damn points, right? What are you going to do with all of this? So when you come into fit model, which is there under model, what you want to do, and I don't have a lot of time here without getting us off schedule, but the first thing you want to do is use these options to get rid of a lot of these points. So if we look at a strict left view, I'm going to come in here and choose by region, and that means I'm selecting a bunch of these points. You can also choose by region by just holding the shift button. So you do that a few times. If there's any hidden behind, we've got them now. And what we want to do is hide all unselected points. So we did that. Now we can get out of the select region. Now you can see we're not dealing with all those points. Now we're just dealing with the points in that neighborhood. And we're just doing this to simplify our life. And so what we can continue doing is, what we really want is, if we want to match this section right in here, what we really want to do is only, let's select none. So now we're back down to none. What we really want to do is just select the ones very relevant, really near, there we go, very near that cross section that we want. So we want to just pare down so that we're only looking at those points. And then we want to develop our targets just for those. So that's one way to go about it. I'm actually going to show a different way real quick. Let's come in here and let's get rid of our cloud of points. Let me close fit model first. Let's get rid of our cloud of points. And when we brought in this, I know I'm going over, and we'll just start the next one a little bit late. No, it's somebody else's talk, so I won't do that. I'll wrap this up quickly. The other trick, this is a really great trick, is if you have a model like this that you can bring in wherever it comes from as a mesh, what I recommend you do is you use planar slice. And here we're doing x-axis slicing, and let's just create, I think 3 is the minimum, and let's not use auto, but we know we want one at 12. So let's go from 10, 3 of them, to 10 to 14. I think if we start slicing, that's going to create 3 slices, one of which is at 12. And the great thing here is that created it as a mesh geom. So first, let's we'll come in here, but we only want to look at it as the slices. And if we do that and we convert it to a point cloud, what we have, okay, that it did both. Let me delete that. So we're going to need to export this. I know this is more steps than it ought to be. So what I do next is I would export this, which is just exporting the shown set. So it's just exporting these slices as an STL. And here, this is just going to be my slice, and I'll accept. And then I'm going to delete that. I'm going to come back in where my import was. I'm going to import that slice back in. And here, now it's only the slice. So now when I convert it to a point cloud and then I no-show it and I show just that point cloud, now you see I have a beautiful ring of points at exactly that 12 location. And so now when I go to fit model and I want to select my points with a box, now I select just those points and I have exactly the points at the 12 location, which I'm going to associate with my fuselage. I'm going to do free. I'm going to add my target points, and it should go through and add all 298 of these points with their association to the fuselage, and hopefully this won't crash. But I hope that gives you some strategies and some ideas for working with sort of an arbitrary cross-section in the middle of a geometry and how to go about matching that. I'm not sure where it's going wrong, but I'm over my time, so I'll turn it over to Brandon.
No, that's all right, and I appreciate that. And if we have some extra stuff that people still want to see demonstrated, in the interest of time, we can always try and append some of this to the end of the day, and it will just be included in the recording after the fact. So let's go ahead and Nat, if you want to share your desktop, you're welcome to go ahead and take off.
Okay, thanks. Let me bring that up. All right, so hopefully you guys can hear me and see my title chart here. I know the schedule says automated meshing, I think, from OpenVSP, and I had planned on doing something along those veins, but I ran out of time with some of the validation to make sure that the meshes were actually working in CFD. So we're doing my other talk here, which is CART 3D engine modeling in OpenVSP, and it probably is even more. Oh, yeah. There we go. So let's get started here, if I can. There we go. So really the motivation for this work, about 5 years ago or so, I was working on a PhD dissertation that centered on understanding the PAI implications of overwing nacelles. So I wanted to have a powered engine model because I was concerned that the exhaust blowing over a supercritical wing would cause a lot of problems, and I didn't want to flow through nacelle, so I had to worry about that. In an academic environment, I started with SU2 because it's free and open source, which is the right price for students. And then after I started at NASA, I moved over to CART 3D. But the whole time I used OpenVSP for the geometry engine to model this whole thing. And so when I got started with CART 3D, the process for making a engine model or a power boundary condition model is you create some geometry, which for me is on my workstation, which is a Windows computer using OpenVSP. And then you take your VSP model, you export a trie file. Then CART 3D is, of course, on a Linux system. And I know all you Mac users will snicker at me, but I have to work between the two systems because our Linux are headless, so there's no VSP on there. So carry it over to Linux, create a Trix, or use the Trix command to create a tech plot file, bring it back to my Windows computer, find certain mesh cell numbers on the faces, in TechPlot, and then take that back to the Linux side. And there's a command called break tries that will find that cell number, and it will separate your watertight component where there's sharp edges. So if you think about like a 90-degree turn, it will find all the cells that are within that plane, and it will break them from the rest. Then once you have your broken geometry, you use Trix again to create a tech plot file, and then you can figure out which surfaces are your flow-through surfaces and which ones are your solid surfaces. Just a lot of steps. I wasn't very comfortable with all of this, especially going back and forth from Windows to Linux. It was kind of time-consuming, so I said, can I just do the whole thing in VSP and not have to worry about it? So we spent some time, and the answer is yes, basically. If you heard one of Rob's talks earlier about subsurfaces, right? OpenVSP has these subsurface features that will break out surfaces into subsurfaces. It tags them, and they'll create separate components automatically. And when I first started this, I had these really small gaps because I would say, hey, look, I want a subsurface. Oops, guess there's no right click. Right along, this inlet geometry here. But based on where my components were in the UV space, they wouldn't line up perfectly. So, for example, if I had if my UV cross sections were every third of a number, so if I had cross sections 0, 1, 2, 3, 4, 0, 1, 2, 3, my cross section UV wise would be at 0, 0.3333, 0.666, and then 1. And you can't put a subsurface at exactly 1/3. It's an irrational number, so it doesn't make any sense. But I could get around this if I perfectly matched the UV coordinates with OpenVSP. And the way I did that was kind of padding the number of cross sections I had. And so this is kind of an overview of what the model ended up looking like here, where you have your spinner, your inlet. This inner surface here is actually a separate surface. So if you're doing your drag bookkeeping, this can go in kind of the engine makers typically count this towards their ram drag, whereas the external nacelle drag gets book kept with the airframe typically. Same thing with the inner parts and so on and so forth. Kind of covered this already, but in general with OpenVSP in the UW space, 0 is your first cross section. It's 0 indexed also, and then 1 is your last, right? So in UV space, your component goes from 0 to 1. It doesn't matter how big it is, if it's 10 feet or 100 feet. In UV space, it's 0 to 1 for the most part. Intermediate cross sections have a U or V coordinated as I over N. So again, if you have cross sections going from 0 to 4, you would have, I would say, 4 cross sections. It's really 5, but with the 0 index, that last one's 4. And so each cross section is at I over N. And as long as 1 over N is rational, you're fine. If it's irrational, you can't place subsurfaces directly on top of the cross sections. So it kind of limits you to how many subsurface or cross sections you can use. Actually, cross section, 2, 4, 5, 8. It goes on, but you get the idea. And if you don't have exactly 16 or 20 cross sections, you can just add more cross sections to the start or the end in order to kind of pad the number of cross sections you have and get the UV spacing where you want it to be. And so if we look, the last chart that I have before I jump into a demo this is what my geometry looked like. This is exported from TechPlot, so it's a little bit cleaner and highlighted. But I had 20 cross sections. That's 21, but it's numbered from 0 to 20. You can control the key areas and dimensions, right? So the inlet area, the exhaust areas, the maximum diameter of the nacelle, the highlight diameter and where all those are located. And for my example, I just used an axisymmetric nacelle for convenience, but certainly if you wanted a non-axisymmetric nacelle, either because you want kind of a droop or something like that, you can do that through skinning. And another feature here is I have blunt trailing edges on the aft part of the nacelle and kind of these cones here, and also the leading edge and trailing edge. So let's see. Oh, I guess the other note I'll make is, and we'll go through this, is getting this curvature right in the highlight region is pretty tricky, right? So you have to just be careful with your skinning in order to do this. But with that, that's the end of my chart. So I'll start walking through a demo here to that one to go through here. So first, right, if we take a fuselage and add it just to really kind of highlight the UV spacing here a bit. There's a generic fuselage. It natively has, if you go to the cross sections, it has 4. So 0, 1, 2, 3, 4. And let's just add a blank and attach it in the UV space. And so it's at U equals 0. It's at the nose. If I move it to U equals 1, it's back there. If we put this at 0.5, it goes to the middle. All right, so that's nothing fancy. But if we cut out some of these, so now we only have one intermediate cross section, 0, 1, and 2. And if we look, that blank, which is right here, is still at U equals 0.5. And it doesn't matter where I move this cross section, that is U equals 0.5. It doesn't matter if that cross section is right next to the leading edge or if I move it all the way back to the trailing edge, that's where U equals 0.5. So U is 0. It's probably a quarter-ish around here. It's 0.5 right here, and it's 3/4, somewhere right there. So it's not linearly spaced, which can be frustrating if you were expecting that. But if you know that's a feature, you can use it really to your advantage on how to do this. And so The next step is here's a clipped view of my engine model. If you turn off the clipping, it looks like that. It's a watertight single component stack. So I use the stack feature here. If we turn clipping back on, so you can see the internals. There we go. Making sure my view is right here. Let's just that'll do. So I'll just walk through this here fairly quick. If we go to the first cross section, it's just a point. Right, the second cross section is also a point. Right, so this is an example of padding. I have 2 points at the leading edge. There's no point in having 2 points to start out your geometry, but it was necessary for me to get 20 so I could do simple math. Same thing, this next one is this intermediate circle. That's just a padded subsurface. I could have, or cross section, could have made that a point also. We go out and I have this blunt spinner. I did that because when I was going to grow cells off of this geometry for SU2, I didn't want a sharp point and have kind of the tricky mesh cells that came with that. So I blunted it a little bit. And then just walking through, right, it comes out to the next one is here, which is the start at the inlet. And then also what I did is I put a subsurface here, the inlet inner diameter. And if you notice that the cross section is 0.2, this is cross section 4, so that's 4 out of 20. And it's perfectly exactly there, lined up. If we look at this cross section skinning wise, the angle comes in along the x-axis, so at an angle of 0, and it goes out at 90 degrees to the x-axis. So you have this perfectly flat inlet face. If you go to the next cross section 5, it comes in at 90 and it goes out at 180, so it's going in the negative x-axis. So here's how you define your inlet. And again, there's another subsurface on the outer diameter. So when this gets exported, this inlet face is its own face. And there's no need to worry about what number it is. It's number 2. Number 1 is the spinner. Number 2 is this one. VSP just orders them kind of in a UV coordinate number. Let's see, the next cross section is right here at the highlight. And this is where you have to play with the skinning and the diameter to look kind of how you want. What I also did, and I'll show you in a meshing example here in a minute, is I put another subsection here at the highlight so that when I export this into a meshing tool like Pointwise or something, it will give me a connector here that I can control the spacing there. That way, right, Brandon talked about in the last presentation, you want to make sure you have enough refinement on your leading edge. You can get that by putting a cross section there. Walking through, next one is kind of the max diameter cross section right here. You could move this forward or after, make it bigger or smaller to change the nacelle shape, or if you had some kind of optimizer, you could probably try and run that through. Let's see, going to the back, here's my blunt trailing edge. It's just a very thin trailing edge on the back, and then it doubles back on itself right there. And I put another subsection here so that I can separate this inner surface from the outer surface for that thrust drag bookkeeping issue. And then I moved it here. And you can, right, obviously, if you want to model more of the internals of the engine, you could move this surface back further to here, but I didn't want to, so I just moved it here, save some cells and things. And yeah, and then it's just repeat the process. It comes out through here. Oh, there is one more feature I want to talk about. Here's the input, the exhaust flow, the bypass flow, I should say. And I put a cross section here, you can see. And it's kind of annoying because it broke up this nice smooth surface that I wanted to have on the nozzle for the core. But doing this allowed me to control the diameter right here. And if I were to line up the view right, this cross section is right located in line with this upper one. So you take the diameter here of 0.918, and if you took the diameter of this point here, you can easily find the nozzle area for your flow. And if you're doing some kind of inviscid solver, you really only need to know the area of your boundary condition, so you know how much back pressure to apply there, and then the area of your nozzle, so you can control the Mach number there. And with those two things, you can pretty much set everything up. Viscous solvers are a little bit trickier, but Cart3D was inviscid, so I didn't have to worry about that for a while. And then after that, yeah, same process for the core. I put another cross section here to give the core nozzle area. And then I think in the back I have a few more cross sections to pad it, so I got 20. Yeah, so then from here, right, if you were to run comp geom, you would get this. I foiled. So when I saved it, it did not work properly. I don't know. I can run this again and show you what it looks like. It'll take a few seconds to load. I guess it gives me the opportunity to say that when I started this, it never works like you think it's going to. Or did I think I comp geom the wrong thing. Let's try this. Show comp geom. All right, let's try this one. When I ran through this invisibly, right, like I said, just kind of eyeballed most of this geometry. It's more or less right, and every engine looks more or less like this, right? The diameters will change, the max thickness will change, the length to inlet diameter, will change, but fundamentally it's the same. When I ran it viscously, I did get separation coming off of this inlet lip because it wasn't designed terribly well. It was just kind of eyeballed, and inviscid calculators don't care. There's no separation. Viscous calculators do care. All right, so here's the comp geom. You could stick this straight into Cart3D and it would run very well. Yeah, you probably should up the tessellation a little bit, but Cart3D is pretty insensitive to that. Make this geometry, you run it, you can test it, you can then go back and, if the areas don't line up to what you thought they were or something, you can just change it and put it straight into Cart3D and run. Very quick. If you didn't use the subsurfaces, this whole thing would just look like this, which is, one single component and it's not broken out and it's not at all what you want. So you need the subsurfaces for that. Once you have this geometry, you can go file export and export as a untrimmed IGES. You want to split surfaces on the UW constraints. Units or meters, sure, why not? Let's just cancel that because I've already done that and I don't want to risk breaking it. But from here, right, so if you have that, you can go into your favorite meshing tool. For me, that's Pointwise. I know Brandon's a big CGT guy, but I'll just take this. Convert from file. It always gave me this warning, can't convert 56 entry entities. I don't know if that's a VSP thing or a Pointwise thing. So really quick on how to mesh this in like Pointwise. It's select databases, select all, and just turn this into what should be a single water type model. But if you go down, you'll look, it's not a single one, there's 4, and it comes down to kind of this region back here. There's a few surfaces that didn't play nice. So we can just take the main one and put it in its own layer and turn it off. And now we can go look at the back of the engine. And I know from experience that these ones back here are kind of in the 2nd, 3rd, and 4th quadrant. Doesn't matter though, we'll just get rid of them. This is, those blunt surfaces at the nose and the tip of the engine. If I have a quarter of an engine now, I can turn this layer back on. It's a quarter of a water type model. You should follow your best meshing practices, but we'll just put 50 nodes on every connector here. Highlight all these and make a mesh. There. So we now have a structured mesh across the entire engine. You can go and apply your best practices as you want, right? If you decide that you don't want quite that many nodes along here, let's deselect that. We'll select connectors. You can always change this to 25. And because it was a structured mesh, all of the radial components here need to be the same. I missed these 2, so we'll change these to 25 also. Have a nice mesh. Oh, I mean, it's not a nice mesh, but it looks good. If we notice here, this is not near refined enough near the leading edge, but because we put a constant U surface here, or a subsurface, we can control the spacing. Just, pick these connectors there, set a spacing of 1 centimeter, why not? And that'll pull points forward. And now we can really control the spacing there. Again, probably not fine enough for what you want, but for a 5-minute demo, this works pretty well. So if you like that mesh, there's your quarter of your engine. You can just copy it and paste it. And it'll ask you how you want to paste it. So let's mirror it about z equals 0. Sure. Okay. Let's do that again. We'll just copy and paste. And this time we'll mirror it about y equals 0. There. So now we have a full engine. It's all meshed how you like. The only thing that's not right is, it couldn't make a structured mesh on this surface because there's only 3 connectors. So what we can do is just make sure I don't get any connections in there. Yeah. Delete those 4, and Pointwise is smart enough to know how to connect a circular mesh. And there. So this whole thing would be a structured mesh if you wanted it. If you wanted to use an unstructured, it's pretty easy. You can either, the lazy way, I suppose, would be to go in here and just diagonalize it. And we'll hide the original mesh. And there, so now it's an unstructured mesh, if that's what you wanted. You could also use, T-Rex, and there's another other features in Pointwise. It's a very powerful meshing program. But from here, yeah, you can grow your 3D mesh from this if you wanted to, using best practices. You can export this to Cart 3D, apply your boundary conditions to these things, these patches here. There's your inlet, so on and so forth. But it works pretty well. And yeah, that was maybe quick, but that was my solution to this problem, and it worked pretty well in getting a realistic engine model out of VSP in a pretty short order once you kind of had the geometry set up. So I'll stop there and take time for questions, or we've made up a few minutes on the schedule, if that helps.
No, that's. Do you have the YouTube video pulled up, Nat?
I don't.
Okay, that's weird. I'm hearing an echo come through on my audio here, but anyway, no, that's really great work. That's a really interesting application of how to break that stuff out, and yeah, really great stuff. So we have about 7 minutes before the next talk.
Hey, Brandon.
Yes, Rob.
I think I'll jump in and finish that fit model demo I was doing during this 7 minutes.
Yeah, of course. Come on back in.
And I don't see any questions. Nat, thanks a lot for that demo. I don't see any questions on either place for that immediately, but if anybody has them, we'll get those forwarded to Nat.
Yeah, and hopefully, someone finds that useful. That was my solution to a problem. If someone else runs into that same problem, they at least know how to work around it, but I hope it helps.
All right. So I know this is jumping around a little bit, but I figured I'd just use these couple of minutes to keep everybody from having to stay late. If they wanted to, I can fix that problem. When I selected all these points, I'd selected them here, and I went to associate them. Unfortunately, I chose to associate them with the original fuselage geometry. And instead of choosing the stack, which is what I really wanted to match them to. So that's why it was taking a little bit longer than I wanted. And it then ended up, they all perfectly matched because they fit the geometry perfectly. So let me just come in here with a stack and say, add the target, and see it's much, much faster there. Oops, I grabbed one rogue point up there. And you'll see that what it did when you add them, since they're free in UW, is it finds the nearest point on that shape to it. And, it may be counterintuitive that the nearest point's here in the middle instead of up here on the front, but that's actually the nearest point in 3D space. But we know we want to match this front circle. So what I'm going to do is I'm going to get rid of all those, and I'm going to come back and reselect all my points. And here I want to fix them in U to U0. So I want to force it to this center ring. And I'm going to add all those targets, and you can see now it's forced. So that's how I would associate these. If I then want to come in and pick my variables, and I'm working with the stack, and I'm on cross-section 0, clearly if it's a circle, then I just want to use the diameter as a way to fit, and that's one variable. And if I do that, I'm just going to say, let's fit it and see how it does. And so given that level of control, which is just the diameter, this is the least squares best fit right here. And I know that's not very impressive, but this is just how the optimization works, right? That's the best it can do. Now, it might be helpful for me to also give it the ability to move this around. And since this is the first cross section, I can't move it in Z and Y at the cross section, so I have to come to the transform. But let's give it freedom to move it in the Y and the Z. And if we fit it again, what we'll see is it moved it a little, and it's a little bit better fit. Our distance metric got a little better. Again, this is not anything to write home about, though, right? This is not impressive because it's not a great fit. So let's say, okay, we know we're going to fit it better. What if we change it to an ellipse? Now, just like with linking, when parameters vanish or things change, it's gonna remove that diameter. So when I change it to an ellipse, the diameter went away, but now I can change both height and width, and now I have an additional degree of freedom to try and fit. So it's going to crunch the numbers and do the best job it can, trying to fit an ellipse to this shape. Again, right now it can't rotate it, but that's the best it can do. And this isn't thrilling by any means. So let's try, we know that a rounded rectangle is going to do better. It's not perfect because this top is still curved. So we're going to change this to a rounded rectangle, and we're going to let it change both the width and the height and the skew and the keystone and the radius. Why not? So we're going to let it change all of these things, and we'll do a fit, and we'll see how it does at matching this. And you'll notice, well, now we're getting somewhere. And in fact, let me increase that. So now we're at least really resembling that shape. We're close. But remember, this was an intermediate cross section. There was a rounded rectangle over here, and it was a circle to the left. And so we've got some blend, and you'll see that, we're not perfect all along here. And so what we really want to match is not fitting it to a rounded rectangle. This is close. It might be close enough. What we really want to do is match it exactly. And the best we can do for that would actually be to convert this to a C-edit. And so the C-edit type is the Bezier curve type. And when we do that, of course, the rounded rectangle is going to get destroyed. So these variables are going to vanish. And we're going to fit the best fit C-edit that we can to this. So when I do that and I convert, you'll see those variables all vanished here. And we've got now a best fit C-edit on this side. And what we're going to do is we can now tweak the X and Y control points in a best fit way. And first off, I know that these are all smooth. These are nice smooth corners. So I'm going to come in here and I'm going to turn on my G1 options to keep these things smooth. And there's a bunch. So let me just, okay, so now we've got a nice smooth shape everywhere. And actually, you know what? I think this is probably too many points. So I don't want to deal with this many. So I'm going to at least come in here. I'm going to delete some of these from the middle. Oh, that was the starting point. So it doesn't really like me to delete it, maybe. So I'm going to delete some from the middle, and that'll probably help. So now we've got kind of 3 in the corners. Let me see if I can delete that one again. Yeah, I don't think I can't delete that because it's the start and the end. But we've got enough of these, and now we just want to choose which ones we want to add. And so we've got the X and the Y points on them, and we don't want to mess with the U points. We'll talk more about that later. But we've got the ability to move a bunch of these points around. And so what we might do, for example, is we might come and say, okay, I want to move this point, which it highlights it for me. This is number 27. So I want to choose X27 and Y27. Right now, again, there's a lot of these, and if I just do an optimization here, notice it tweaked just that part of the geometry to do the best it could. So in this case, coming in here to a variable tree, it's going to be a more efficient way of doing it, and I'll be quick just to show you how this works. But we're working on XSEC curve 0. And then we're coming in, and here's all these points, right? And look, there's my X and Y, which they're numbered 33 in here. And that's, as you delete points, these don't get renumbered the same way these get renumbered. So that's why the numbers don't match. But I can just come in here and say, you know what, I want to pick some more of these X and Y's. We just know we want a bunch of them. And this is a really fast way to do that. X, Y's, X, Y's, X, Y's. I love my X, Y's, right? Just choose a bunch of these. And we're adding all these to our fit model process. And that's probably enough. And when I hit fit, you'll notice all these just got adjusted. It looks like it did something a little weird there. I'm not super thrilled with that. Let me try and adjust those and fit again to see if that helped. So something's going weird with the optimization process. I'd have to look at what I'm doing in here in terms of this fit. This point in particular is out of whack. So I'm going to grab that one and bring it back in. That didn't make sense. Let's see if it does it again to us. So some of these, so there's some ringing that's going on, but that's all I've got time for here. But it shows you the process of how you should be able to go in and use this kind of a section to match that curvature if you really need to match an arbitrary section that you didn't see otherwise. And from there, I'm going to go ahead and jump into what's scheduled for this hour.
That's going to be the talk on design variables and variable presets. So if anybody has anything that they want to cover in a few minutes, this one can be a long talk, but it can be relatively simple depending on how deep you want to go down the rabbit hole. So by all means, add some questions to the social Q&A. Everybody remember to set to 1080p if you haven't done so already, and we'll keep watching the chat. So Rob, it's all yours.
All right, thank you. So we've got, again, another kind of grab bag of topics. The design files and XDDM for Cart3D optimization go together. The variable presets is kind of related. It's an interesting feature, and we'll spend some time talking about that. I'm Rob McDonald, and thank you all for joining us for this session of the VSP workshop. First, let's talk about some typical design workflows. Lots of times you'll use a VSP model as a baseline, and then you'll want to go and make changes to that model to try and design a better aircraft or a better model. And so you can do this lots of ways. You can do it through the API. You can do it by building your own models. But one of these workflows was so common that we added this design capability that I'm talking about today to try and make that easier. So the idea is, the first thing you want to do for a typical design workflow is you have to set up the design problem. And so that's done interactively. So the setup, you load or create a baseline file. Then you choose the variables that you're going to participate in your design study. You save a design file, and that writes out either a DES or an XDDM file. And that sets up your design process. Then, in your design study, what you do is you modify that DES file. You make changes, and that's basically a template. You modify that, maybe you do it in MATLAB, Excel, Python, whatever you want to do. You modify that design file. And then from VSP's standpoint, the red boxes are VSP. You load the baseline file, the same baseline file is over here. You load the modified design file. You perform some operation. You generate a mesh, you do comp geom, you do a drag calculation, whatever you do. You perform that operation, and you get your result of your design. And that's the typical kind of workflow that you might do as an iterative that we're trying to support. It also allows you to do an inspection. So let's say you've done this design, and it's come through until you got to an optimal airplane. Now you want to look at that airplane. You want to see what it looks like. So in that case, what you do is you take your modified design file of your optimum, your final answer. Again, you load up the baseline file interactively. You load the design file. It applies those changes, and then you've got a normal interactive VSP session from there. And hopefully this will make a little bit more sense as we go forward. A little bit of an aside, Cart3D, which is a CFD package from NASA Ames, has an adjoint-based design capability built in. And in that design capability, that part was really developed by Marian Nemec. Marian developed the XDDM format as a way to describe the optimization problem. So that's how you tell Cart3D what the variables it can vary and the min and the max values for those for optimization. And I think XDDM means XML Design Data Model, I think. No, it's right there, Extensible Design Description Markup. So this is just a Cart3D special format, but it contains the same information as the design file. And it contains, these elements of a variable, a constant analysis, all this information for Cart3D, and some other things that go with it. And so VSP now has native support, and has for a long time, for Cart3D shape optimization. So it makes it trivially easy to use VSP as the geometry engine in a Cart3D optimization study. And it just does what you want it to do. So that's fun. So like I said earlier, to do this, you go to the model menu and you choose design variables, and that loads up the design variable GUI. And for a particular design study, what you're going to do first is you're going to choose which variables you want to work with. And so you can use the pull downs, or you can drag and drop, and you just pick. You say, okay, I want to vary root chord, span, sweep, tip chord. You add those to the list, and it's just that easy. You've set up a design problem. After you've chosen them, well, here's that just zoomed in. You can pick on the top. You tell it whether it's a variable or a constant, which is an XDDM flag. You can add or just drag and drop. And then down here at the bottom is where you save or load that file. And you either do an XDDM file or a DES file, and then you save that file. The other tab, when you pick those 4 variables, that gives you just a handy place where you can go and you can adjust those right here without having to go anywhere else. So you can also use this as a way to just pull. If you've got 5 variables that you love to vary on a particular model, and one is on an engine, one's on a pod, and one's on a tail, you don't want to have to go searching around for them when you're presenting to your boss. So you can just come in and consolidate those in one place to make them easy to find. The design file, the DES file, is just this incredibly simple text file. The first line is the number of variables. Then each line, there's 1 per variable. It starts with a unique ID that comes out of VSP. It's all caps. It's probably 11 characters long, maybe. And that's a random generated ID that you don't want to change. That is what VSP uses to uniquely identify the variable. After that is the human readable name that goes with the component name, the group, and the parameter. So that's that hierarchical name that we work with. And then after that, there's a final colon with a space, and then the value, the number. This is a very simple file. If you're doing a design study in MATLAB, what I would do is I would set it up so that it just prints these 5 lines with whatever numbers you want as the final bit. And that's all you have to do to write a design file, a DES file. XDDM is the same idea, but it's Merriam-Webster's format. It's an XML, so it's a little bit, it has a lot more greater than and less than signs in it. This is how it gets set up. Here on the left, there's an ID, and this ID is the name that Cart3D is going to name it, and the optimization framework is going to name it. We default that to the component, group, and variable name. That's probably more verbose than you want. It's a big ugly name, so you may want to trim these down and edit them. So change it to whatever you want. Call it just chord, span, sweep, and tip, or whatever you want. You can change these. However, over here's the VSP ID. These are that random number, that random letter ID that we use internally in VSP to uniquely identify the parameter. Don't change these because then it won't work. So this is what VSP uses to uniquely identify the parameter. This is just a label that Cart3D and the optimization framework uses to report out to users what's going on. Once you've done that, you can now access these from the command line for your optimization study. So for example, if you run VSP with the baseline file, airplane.vsp3, and you want to run a script, whatever your script is, it will, this is the command line help that VSP spits out. So if you want to just write out a Cart3D and unintersected try file, that's actually just a 1-line script. I mean, 5 if you count the comments and things like that. So you just have to have a main with export file, the output.try 0 is the set all, and then what type is export Cart3D. And this script, if you run it as the script, will output that file. Likewise, if you want to run CompGeom and then export, it's 2 lines, or if you want to run CFD mesh, it can just be 1 line with all the exports set. And you can use that and apply it with a DES file or an XDDM file. Changing gears a little bit, there's this concept of variable presets. And presets are a neat technique where you can have a single model that now has multiple states in it. And it's different versions of a single model, but all in one file. So certain things can't change, right? It's going to have the same number of fuselages, the same number of wings. They're going to have the same names. They're going to have the same number of cross sections, the same airfoil types, the same exec types, right? So that level, that the topology of a model stays the same, but the values of the parameters, anything you can move with a slider, they can be different. And that's the state difference. And you can use this for all kinds of things. For example, if you have articulation in your model, you can have different states of articulation. So you can have a gear up model and a gear down model. If you go to the trouble of modeling flaps, you can have a flaps down, flaps up, and you can have different flap positions. You can have takeoff versus landing deployment. You can have your wings folded and deployed, tilt rotor or variable sweep in different positions. So those are all articulation things that'll be different states. You can also make different tweaks for different analyses. For example, maybe you run 2 different analyses, 3 different analyses, and you want to use different mesh resolutions for these. So you can have one state which is sort of set all of the tessellation parameters to fine, and another that sets all of the tessellation parameters to coarse. And you can very easily switch back and forth between your fine model and your coarse model, or your medium model. Another use is when you're doing a design study. In any sort of design study, you're going to have a baseline model, but after you've completed the study, you might save as a preset your answers, and you might have multiple answers to an optimization study. You might have a minimum mass, minimum gross weight vehicle. You might have a minimum fuel burn vehicle or a minimum cost vehicle. And using variable presets, you can very quickly switch between the different versions of your answer. You can also use it for a family of airplanes. And depending on how detailed your model is and how simple it is or how you set it up, you could just do a variance of a family like a 737-7, -8, and -9 and have one model that represents each of those. You could probably, not in super fine detail, but you could probably also do a single model that represents most twin engine transports, whether they're Boeing or Airbus or a Sukhoi or a Comac, and you'd be able to capture most twin engine transports with a single model that gets pretty close just by varying some of the parameters. So these are all different things you can do with variable presets. And again, this is a power feature. You'll know if you need it, and it'll really enable you to do some cool things as we go forward. The way it works is variable presets operates on groups of parameters. And so you're going to group the parameters into something like landing gear or mesh resolution. You're going to give it a name. So a group is named. You get to pick the name. And then there's multiple parameters in a group. So if you have landing gear and its articulation, you're going to have one that rotates the nose gear and a different one that rotates the main gear. So you've got multiple parms in a group. And of course, parms could be in multiple groups, but that probably won't actually happen. So you've got groups of parms, named groups of parms, and then you have each group gets different settings. So if it was a landing gear, the obvious settings are going to be up and down, and they get names. If they're flaps, then you might have cruise, takeoff, and landing as the 3 settings that are named. To set one of these up, the general workflow is you first add and name a group, then you add and name a setting to that group, and you pick what parameters you want to be in the group, again, either through the pull down or through drag and drop. And then you can add more settings and give other sets of names. So you can rotate through that to set it up. Once you set it up, it's really easy to work with, in that if you want to switch, you just come back to the variable preset menu and you say, which group do you want to switch? Do you want to switch landing gear or resolution? And you want to then apply your set. You pick which setting you want. I want to set my landing gear to takeoff or to cruise, and then you hit the apply button and it sets all those parameters. So that's how the workflow works. To get to it, you go under the model tab. You pull down variable presets. Right now is the last one on the list. So you choose the variable presets menu. It pops up like this. This top part, this very top part, is where you, if you're just coming to switch models, this is where you pick the group and the setting and you hit apply. So this is where you work once you want to change the parameters. Everything down here is more for setting it up. So you can create or adjust the values. So here's where you can add a group, then you add the settings and you pick what variables are in it and you set that all up. So with that, I've got time for a little bit of a demo. I can do both a design flow demo as well as a variable presets demo. If there's any questions that are coming up, Brandon, you can ask them and I'll try to answer it as I go.
Okay, there was a question that did come up that says, can you use variable design files to change mass properties directly from MATLAB, or presumably with any editor?
On the third day of the workshop, Thursday, I guess, Justin will be giving a talk about using MATLAB from the API, so you can really talk very directly. So that's a pretty advanced thing. So you can certainly do that. I think a lot of people don't need to go that far. And what I would do is I would just use the design file, and I would, like that example I showed earlier, it's just 4 printf lines, and so you'd have your MATLAB script with 4 lines of printf, dump out that file with whatever values you want for the variables, save that file, and then you can then execute VSP using the system command to run an external program. And so that's probably how I would do it from MATLAB. Let me just do a little bit of a des file demo. So here's the default wing. And if we're only working with the wing in our design study, we come here to our design variables menu. And here's the design variables thing where we get to pick this GUI where we get to pick what variables we care about in our design study. So in our design study, for example, maybe we care about the span, the root chord, the tip chord, and the sweep angle. So all we do is we just drag and drop to pick which variables we care about. As I said, they all get added to this adjust menu. And so I can come in here and I can change those all from this one place. And that just consolidates them. If, once you've done a study, you want to come in here and you don't have the component open, you can still vary these. Down here at the bottom is where you save or load that file. So let's save this. And actually, before we do that, let's save the airplane. So we're just going to save it on my desktop as our desvar demo VSP3. So we just save that file. And now we want to save, we're going to save a des file. So we're going to do test des and we'll accept. And we'll also do the XDDM. Whoops. Let's change it to the XDDM, and we'll do test. And we'll call it test2, even though it's going to give it the XDDM name. So, here we are, VSP's loaded. We could quit if we wanted. We could do this from the command line. But what I'm going to do is I'm going to come over here, and I'm just going to open this des file with a generic text editor. I like TextBait. And so we'll open it up. And like we said, there's 4 variables. We've got this random string that identifies the variables uniquely. This is the label that tells me what it is, and then here's the values. So let's change our tip chord to 3.5. Let's change our sweep to 22.5 degrees. Let's change our span to 12. Let's change our root chord to 5. And again, however I write this file, whether I'm going to just hit save. So I've now modified this file. However I write this, whether that's 5 lines of printf in MATLAB, or whether that's out of an Excel sheet or Python, however I do it, I write this file. In VSP, I can load this on an automatic way from the API, but to just show you what happens, we can also do it interactively. So this is that third column of that workflow. We can just come and we can hit the load button, and we choose, we are loading an XDDM, instead we want to load a DES. So we load a DES, and there's our file that we modified. And as soon as I hit accept, you're going to see this model update. So I'm going to let you see that, but here we go. We hit accept, and the model updates. And if we come look at the parameters, they're exactly at whatever I set in that file. So that's a typical DES workflow. We'll look real quickly at the XDDM file just so that you can see what it looks like. Conceptually, it's the exact same thing. It's just, instead of in a simple text file, it's in Marion-Nemec's XML format. So this is, you're only going to use XDDM if you're a Cart3D user. Everybody else use DES. But if you're a Cart3D user and you like to do shape optimization, then here's where you can control that. Again, here's the values of what we set them to a minute ago, the min, the max, the unique ID. Again, we can come in here and we can change this to anything else. So if for our study, we want to shorten these names down to root chord, span, sweep, and tip chord, that's a very reasonable thing to do because it's much more human legible. Here we can change our values to anything we want. So let's make the root chord be 1. Let's make the span be 3. We'll make the sweep be -16. And we'll make the tip chord be 0.8. And we'll leave everything else alone, but we'll just hit save. And coming back in here, just like before, if we could switch to XCDM and we load that up, it's going to modify that model to whatever we had. So that's a couple of design workflows. The other one that we talked about here was variable presets. So this is kind of related. What you do is you come into the model. The last option is variable presets. And again, what we're going to do here is we're going to set up 2 groups. So first, let's set up our group, and we'll call this our study variables. We're doing a design study, and we'll call it our study variables. And our first setting is going to be the baseline. And we'll add that. And so now we can come and we can choose what are our variables. And just like last time, we're going to pick span, root chord, tip chord, and sweep. And the values, if we do this right now, they are what they are. If we come in here and we adjust them, really what we want for our baseline, we'll say is a root chord of 4, a span of 9, and a tip chord of 1. And that's the default VSP wing. And we just changed it, so we're going to save the changes. This button, that's going to apply that to our baseline. So when we hit save, it grays out. What we just did is we just updated our baseline. So now our baseline is the baseline wing. And what we're going to do here is we're going to make a fast answer. So when we come in here to what fast means, we're gonna make this look like a fast wing. So we want more sweep, and maybe we even want to go like a delta, something like that, and we want a lot less span. So we're gonna really increase the sweep here. There we go. That looks like a fast airplane to me. So we're gonna save that because that's fast, and we're gonna come back over here, and we're also gonna create slow. And, a slow airplane, if we want to come over here and adjust it, well, that's going to have no sweep at all. And it's going to have a root chord and a tip chord that are the same. And the span is going to be about like that, maybe a little higher, 12. So we've got a nice high aspect ratio Hershey bar wing. So that's our slow airplane. And that's how we created our study vars. But we also wanted a different group. So we're going to create a group that's resolution. We're going to add that, and here we're going to have our baseline. and we'll add our baseline, and it's going to have num_u and num_w, and that's set up as the baseline, so we're fine with that as is. We're going to create fine, and for fine, we just want to come over and say, you know what, we need these to both be a lot bigger. So we're going to make that resolution really fine, and we're going to make this resolution really fine. So that's fine. We're going to hit Save Changes. And we'll also create course. And we'll add course. And again, we'll come in, we'll adjust to whatever we want course to be, but we want it to be really coarse, right? Something really, really chunky, and we'll save changes. So now what we have is, and we can come back to the create tab, it doesn't matter, but we're only going to work now that we've set up our variable presets. And again, these get saved to our model, so we can hit save. Now our model has different states memorized. And so, for example, if we want to go to the baseline resolution, you just choose which group and what setting, and you hit apply. And likewise for our study vars, if we want to look at our baseline study vars, we look at that, and we've got the baseline resolution with the baseline wing. And if we want to change our resolution to fine, then we just change that group and change our setting and hit apply. And likewise, we can look at the study vars slow airplane and look at it fine. And you can just very quickly jump between whatever group and whatever settings you want to apply for variable presets. I think that's probably enough of a demo. If there's any questions, we've got maybe 3 minutes for questions before we need to start the last talk for the day.
Okay, thanks, Rob. We had somebody send a message here asking if, when you're using the design variables, if you add multiple component masses together to get a total mass, would you either control the total mass or the incremental masses in the des script? So, for example, the wing itself plus something that's electrical or hydraulic.
So that's more a question about how masses work in VSP.
Yeah.
If we come into the wing geom, we don't have a talk on mass properties, but VSP will calculate the mass properties for you based on the shape, and it'll have two terms for each geom. One is a volumetric based density, and that's what you think of normally as density. And here it defaults to 1. But, we could change that to 5. And again, the units are going to be whatever you think they are. So if your model's in feet and you want the mass to be in kilos, then this is going to be kilos per cubic foot. So that's 5 kilos per cubic foot. That seems like or kilos per cubic feet. Well, that's what you want it to be. That's what it is. So that's the volumetric density. There's also, you can turn on the thin shell. So any part of the exterior shell, and it's only going to use the shell that's actually in contact with the flow, the wetted surface. So if you have a thin shell, you could use that, and then you're giving a mass per area. So think about this: if you had something like a foam core composite wing, you'd put the foam density in the volumetric, and you'd put the composite layer on the shell. You can then also have other components like this pod. So for mass properties, one way to go is you come in here to mass properties and you say compute. And what this actually just did was it created this text file that shows, here's the mass breakdown, the totals, the center of gravity, the moments of inertia of this geometry, using those densities and surface areas and intersection for the mass properties. So in this way, mass properties is an output, not an input. And that's how we usually think of it in VSP. That said, if you want to treat it as an input, you could certainly, first off, you could have this density as an input that you vary with desvar. So just as I dragged and dropped in design variables, this density could be one of those variables that gets varied. You also could do a blank component. There it is, blank. where you can then attach that to the wing, or say you have a complex model of an internal combustion engine, you could then attach a blank model to it and then come over here to mass, turn on the point mass and drag that down, because you've got a complex model of an internal combustion engine. You don't want to trust VSP's estimate of the mass. The manufacturer tells you that it weighs 167 pounds. You just want to come in here and type in 167 pounds. And so you can drop that point mass in and set the density of the engine and the other components to 0. And now with that point mass, yes, you can vary that mass from a design variable. You can change that engine's point mass from a design variable. And that's a place where mass could be an input for a design study. And I hope that answers your question. I'm going to turn it back over to Brandon.
Thank you very much, Rob. We sure appreciate it. And up next for our last talk of the day, we've got Nick Brake from ES Aero giving a demonstration of OpenVSP's Parasite Drag tool. Nick, are you there?
Yeah, I'm here. Hopefully you can hear me.
Yep, we can hear you and see you. Thanks, bud. And go ahead and share when you're ready.
Great. Yeah, so let me share my desktop here. And we'll walk through the kind of a walkthrough on the Parasite Drag tool, and some of the features, key modeling, and then we'll go through a real quick simple demo, a couple of simple demos, kind of a walkthrough on a simple airplane, and then go through the validation case, which is the S3 Viking. Yes. There we go. Is that better? Okay. Objectives for the development of the Parasite Drag tool, really to, for anybody who's done a Parasite Drag buildup, a traditional workbook method, you use big, long spreadsheets, big, complex spreadsheets to capture everything that you want. And so a lot of a bookkeeping exercise. I took a snapshot of the drag workbook that's up on the VSP OpenVSP wiki page, and that was a really good initial connection between an Excel workbook and the OpenVSP geometry. But when we started to look at developing the Parasite Drag tool, we wanted to go a step further. How can we make this even faster, more accessible? Reduce the time it takes, improve geometry fidelity based on traditional just workbook only methods, provide a validation case to help build some artifacts and build confidence in the tool, allowing people to have it be their go-to tool, and then to make this scriptable, so that you can start exploring the design envelope, different trades on initial trade studies. So those were our initial objectives going forward with the development of the Parasite Drag tool. Our approach was to basically bring a lot of the workbook method into the OpenVSP GUI, and really provide kind of a very familiar interface. So you see this a data table layout that a lot of people are used to seeing in a Parasite Drag buildup, and a lot of the common parameters are right there in front of you. So uses existing geometry equations. It uses existing VSP geometry, friction coefficient equations, form factor equations, flow conditions to get that overall buildup. Try to do provide a good amount, a good variety of those equations to allow the users to select their favorite, or the one that's most applicable for their particular design case. And then we've got the ability to export to a CSV file. So if you do want to bring it into another tool, be it an Excel workbook, be it another analysis tool or a MATLAB script that wants to read in a CSV file, and provide some documentation cases. And I'll go over where that documentation and where the validation cases are available. A little overview of the GUI. Over here on the left, we have the overview tab. This is where you're going to select, what geometry set you want, the typical shown or any of the sets in the set editor. The model length unit. A lot of the equations are based on. This is really one of the tools that really starts requiring a unit here for length. And so if you've modeled in feet, you can select feet. If there's inches, meters, a variety of units here available. The equation selection for friction coefficient for the laminar and turbulence is next, and then reference area right after that. And you can set reference area from model as needed, or you can set it to manual here. And then the flow condition, there's also a variety of different flow conditions that you can specify. The US standard atmosphere is shown here as the default condition, and you can change various parameters here, and even change this around to reflect maybe the condition on Mars, or maybe the condition in a particular wind tunnel, if you're trying to match some wind tunnel results. And then at the very bottom is the main execution buttons here, to allow you to calculate the parasite drag, and then the main other action is to export down to a CSV file. The buildup table here on the right gives you just a summary of all of the geoms that you have in the selected geometry set. And then their buildup onto the right. You can sort it by component, you can sort it by wetted area, and you can also sort it by percent total. You can select some different groups here, different grouping treatment. The form factor equations are settable here, and then you can set percent laminar flow and the interference factor. And then there's also some additional settings depending on the group and form factor equations. The excrescence tab is right here next to the overview tab. You can see as you switch from overview to excrescence to documentation, the buildup table always remains kind of front and center. So you can see what your changes are doing to the table, and how the excrescences are getting added in. So it's always front and center. The excrescence list gives you various options for adding additional drag that's not represented by particular aspects of the geometry, drag counts, drag area, percent margin. Those options are all shown here, and I'll walk through adding some of those in a demo of those. And then next to the excrescence tab is the documentation tab, and this gives you kind of a quick reference for what are the parameters. So you don't necessarily have to go to an external site. You can go look up what some of these symbols are, what they mean, right here within the software. And then down here, there is a link to the wiki, which further documents the parasite drag, the equations used, and references. As far as the equations that are used, for the laminar, there's only the Blasius equation, and then turbulent, you have several other equations here. A lot of the in-depth information here is provided on the parasite drag wiki. I won't go into any of these in detail, but I'll let you. It is available on the wiki site. And then here's just a comparison plot of those different friction coefficient equations plotted against Reynolds number. And a lot of them line up fairly on top of each other. I think in the first iteration of early iterations of the parasite drag tool, there was an error in some of the equations. That's since been fixed. And here's the latest version of the friction coefficients. Form factor equations used. There's also a plethora of different form factor equations. Again, a lot of their references and detailed information are on the wiki. Several different ones for the wing, as well as for body type components. And their plot is shown down here in comparison plots.
Hey, Nick, I'll jump in. There were some bugs with the implementation of these when these plots were made, if you both for the form factor and the CF equation. So if those haven't been updated, they look a lot better now.
And then one other common item that I did want to point out here is the geometry alignment. The tool doesn't make any to be very quick and easily accessible. The tool doesn't make any distinction between a pod. It assumes that pods and wings are aligned with the flow direction. So I just put two different pods into a particular model and ran them through the parasite drag tool, and you can see here they come up with the exact same drag contribution. There's no deriving or inferring the pod orientation angle. And so when you do put a pod in, or you do put a wing in, or if you're using a fuselage component to represent a landing gear strut, or a stack component, those things are going to, when you have those complex geometries, the parasite drag tool is going to assume that it's aligned with the flow. A fuselage would be aligned longitudinally with the flow. So be careful there and make sure you have the expected results that you're wanting to see. For instance, if you are trying to do that landing gear strut, like a typical kind of a bent aluminum landing gear strut that's on a Cessna or something, modeling that with a wing component would work fairly well to align with the flow. I just take you through an order of operations here, going from adding the geometries in the basic OpenVSP geometry browser, getting your model set up, and then coming into the parasite drag tool. You get here by going to the analysis menu, going down to parasite drag, and this window will pop up. You'll select your geometry set, what units you're in, your equation preference, and kind of fall through this list to edit your options as needed. Then you'll then go through and over to the excrescence tab, add your excrescences as you have them defined, and then go ahead and set your flow conditions. And if you want to change your various atmosphere parameters, and then the final step here is to come in and calculate your CDO, and that'll allow you to just get the quickest way to get into your initial buildup. And then you can go in and when you hit calculate CDO, if you have a really complex model, it does run CompGeom behind the scenes when you click on it. So it may take a few seconds to go through, depending on how tessellated your model is. And then the table will populate, the buildup table will populate to the right. So just give it a minute. If CompGeom works, this tool should work just fine. And then you can use the scroll bar. Scroll bars will pop up kind of as needed, and to see the rest of your options. If you come up with the final results and you see, oh, where are the rest of my items, it's likely that your window just got size just isn't capturing it all. So you can scroll to the right. I've also found on some monitors just slightly resizing the window will allow everything to pop up. Microsoft Windows seems to refresh and get the right size, figure out the right size of the window. The changes to the free stream properties can be adjusted. Changes to interference factor, things, those can all be adjusted. Addition of excrescence can all be adjusted after calculating the CDO. But if you do change geometry, like changing the wingspan or changing a pod length, that you'll need to rerun calc CDO, and so it can rerun CompGeom and get new wetted areas. So that'll be one thing. Some stuff you can change on the fly without having to rerun CompGeom, but sometimes you will need. Safe result is to just kind of quick calculate CDO, just make sure you've captured everything that you do want. So I want to take you guys through just a simple demo before I get into the validation case here in a second. Bring up my new version, new instance of VSP. And so for this demo, we'll just add everybody's favorite airplane, a pod and a wing. And we'll add at least one more wing and move it to the back. And here we'll want to add, we can add a control surface. And you'll see that subsurface pop up in a minute here. So going to the analysis tab and pulling up parasite drag, you see that the GUI populates, and you can see that some of this isn't sized, doesn't come up. Kind of quick trick here is to just resize your window, and sometimes that allows it to pop up. I also did notice changing one of these boxes allows it to resize again. So once you got your kind of window all set up, you can expand these. And as I expand this aft wing geom, you'll see the subsurface did come up. And that allows you to give it some separate treatment for that particular area, or set it to a zero drag area. So we're going to do all shown geometry. Let's say we're in feet. We'll do from our first wing geometry, and we'll just go down to 250 feet per second. Calculate CDO, and you can see that this takes a minute, but it did go through and populate. And then you can adjust interference factors, and those populate in real time. So you don't necessarily need to rerun calculate CDO. And then you can sort by wetted area, you can sort by percent total, and back to component. And there are, it will come up with the available form factor equations here as an option, and you can go through and pick your favorite form factor equation, and that you'll see that the answer is populated without having to run calc CDO again. Going to one of the validation cases that we looked at developing this. was a Lockheed S3A Viking. There was a technical report that provided a nice build-up, component-based build-up, traditional drag, with some based on some wind tunnel test results. Quite a few hours of wind tunnel testing. This was done back in the early 1970s. The reports down here, I was able to get aircraft dimensions from this reference, and they did find a reference to the specific airfoils being used at the root and the tip. And so that's what I based the VSP model on here. And then I did two, you can see the nacelles here are bright green. I modeled those in two different ways, and I'll go through those in a second. But this model I did upload up to the VSP Hangar if you guys want to follow along. The VSP modeling, I approximated it from just a basic 3 view. It took a little time tweaking the model for the workshop this year. I updated the airfoils, adjusted the layout to better match some of the images. And then I added the aft nacelle as well as the wing pylon. Those were also referenced in the wing pylon was also referenced in the paper. So I wanted to make sure that the model was complete. And then the cowl or the nacelle was modeled both as a body of revolution and then as a duct. And you'll see the differences or between those two. The nacelles were also modeled with a zero drag interior flow. So I set a subsurface here on the leading edge, a rectangular subsurface that goes basically from the leading edge to the trailing edge for the whole inside of the nacelle. I did that for both the bypass nacelle and the aft nacelle, aft duct. And you can see those here down in the parasite drag. And then for the body of revolution, I built up through the parasite drag tool, built this up and then exported the results to a CSV. I only cleaned it up a little bit by adding some borders here, so it dropped into the presentation nicely. But this is basically what you get out of the parasite drag tool in terms of just opening up the export in Excel. And then I also added here on the right the reference CD, the components from the report, as well as the difference between the report and the parasite drag buildup. In total, this was about 10% off, 10 to 11% off. The excrescences here I included directly from the report, so those match with zero error. But the geometry, just based on the geometry with the body of revolution, we're getting about 11% error. The one thing that I didn't do, because the paper didn't reference in terms of the percent laminar flow of any of the components or any of the interference factors, I left all of these at the default factor. Now I know that's optimistic in terms of the drag buildup. So for what it's worth, those are all documented here, and you can kind of play around with how well using your best engineering practice. I'll leave it up to others to see how that impacts. And then the duct model. You can see here had to change the form factor equation type, and then but overall this matches about 1% better than the body of revolution model, just between the two cases, and you can see going up and down. Overall, getting this within about 10% without adjusting for any of the interference factors. Certainly we are under predicting here on the fuselage component by about 20%. That can easily be taken up by having to add in the 20% interference factor here. So far, for kind of a quick and dirty tool, this turned out fairly well. And then I did from the 2019 VSP workshop, this item right down here, the wing store pylon, that one's a new one. I did put that in, and the geometry is up here as well. So you can play around with that and look at that. And then, as I said, the model is available on the VSP hanger. And I set the source quality good for a drag buildup, and based on just publicly available 3-view drawing. I'll just show you guys. I know I've got about 4 minutes left. I'll show you my VSP model here. So this is the S3 model here, and I have the body of revolution no show right now, but those are essentially the same, pretty close to the same surface. I have them pretty highly tessellated as well. So it takes a second to run the parasite drag tool. But I have a couple of sets set up in here so that I can switch back and forth, and then the flight condition in here as well. You'll see as I click Calc CDO, this takes a second to run, because it is running CompGeom in the background, and calculating all the new wetted areas. As soon as that's done, it'll populate all the wetted areas, and then you can see this is in this example, I have the subsurfaces here that are treated as zero drag, and you can feel free to click those and see how you can set it the same as the parent. Separate treatment. Is it clicks? It's still pending. Or to zero drag. And then it gives you the kind of the real-time buildup down here at the end. And then the export down into the CSV file, just opening this up. This is what it gets you right out of the CSV file. And then you can pretty this up again, and you end up with these tables. So it gives you a very quick way to go through and get your first parasite drag buildup, and get some initial results, get an initial CD knot, so you can move on to other tools like VSP Arrow. And all of this is integrated with the API and scripting, so you can call it. You can call these analysis functions from the API. You can set up each one of the equations through the different enumerators through the API, so you can automate this as you're automating different designs. And there is a set of unit tests that go and plot the data for the atmosphere, the form factors, and the friction coefficients. And then again, the documentation is available here on the OpenVSP wiki. Any questions?
Thanks a lot, Nick. Someone did bring up a question as to what the difference between how VSP Arrow is calculating parasite drag with its kind of basic setup to add that in, and the capabilities of this. Now, obviously, this is quite a bit more detailed and gives you more design freedom, but do you recall off the top of your head what the formulation for parasite drag is in VSP Aero, or will we just leave that for Dave tomorrow?
Let me answer that one.
Okay.
So VSP Aero only calculates parasite drag in vortex lattice mode. It doesn't do anything in panel code mode. In vortex lattice mode, it will it actually does something similar to this for both bodies and wings. For bodies, it has a simple skin friction Reynolds number equation for turbulent. It calculates the Reynolds number on the body. It calculates the local velocity of the component as a whole, and it calculates, and it has a form factor and that it calculates for the bodies. For wings, it actually treats the wing, and also for rotating propellers and rotors, it treats the wing as in a stripwise manner, calculating the local velocity, the local Reynolds number, and applying a simple, it amounts to a form factor, but it's essentially data based on an ACA 0012 out of theory of wing sections. For a full airplane, I think it's reasonable to say you could just ignore the parasite drag out of VSP Aero and use the parasite drag buildup instead. This will give the main advantage that any other excrescences that you are including, like if you're adding in antennas and landing gear and flap gaps and roughness and things like that that are not actually modeled by the physics, you'll have a way to capture them. However, the one really, really great thing about the one built into VSP Aero is when you're doing something like rotating blades on a propeller or a rotor, it's able to calculate that local velocity coefficient, that local velocity and local Mach number and local drag as the velocity varies out the radius of a blade, and calculate that drag so that it actually increments the power required of the rotor, based on that parasite term, not just the induced term. And so, and that's of course something that you wouldn't even be able to get out of a normal airplane analysis for that parasite term. So Kenny and I have talked about it, and we think that, you know, in the future we'll want to go towards sort of a hybrid mode, because of course that VSP Aero model doesn't know anything about all of your excrescences, and since it's just a vortex lattice, it doesn't know anything about anything you leave out, like any booms or landing gear or other components that you leave out of the model. So we eventually need to go towards a way where we use part of the parasite drag analysis and feed that as a basic drag term into VSP Aero so that it gets rolled in. But right now they're separate things.
Thanks a lot, Rob. That was a really good distinction to make, that rotating bodies and things, it does add that stuff in. So I appreciate that. Let's see. We don't have a whole lot for...
We had one more request to do a little more fit model demo. I can stick around for a little bit longer if there's no other questions.
Okay. Yeah, we can do that and let this run for a little bit.
Okay. So there was a request to do the fit model demo I did earlier, but without taking a slice first. So let me see if I can pull that off. There will be a little bit of a different strategy. So we're going to, like before, we're going to import the STL, and I think this was the thing that we were working with. And I'll just go straight ahead and convert it to a point cloud, and I'm going to delete the mesh. So now we only have the point cloud, and we wanted to match something before. We were using a stack, and as you'll recall, I went in before and I cut it down. I actually, oops, I went too far. Let's make this a 2-circle, and I'm going to add an intermediate one. And for now, let's move this to Let's move this to location at 10, and then the XSEC will put a delta of 2, and for the next one we'll put a delta of 2. So again, we wanted to match that location at 12, so we know this section is at 12. That's what we want to match, but we're not going to have a super simple way to do it. So let's quickly turn on symmetry and turn this stuff off. I'm just trying to simplify this down a little bit. Okay, so now we've got something that's a little bit simpler. And while we're at it, we can shade it, and we'll look at it in transparent. So that's kind of a nice way to look at things when you're doing fit model. So to start with, what we're going to do is since we really are just trying to match this middle cross section, we're going to start by just trying to select points near it. But you're going to find that you can't actually do that. You can't just match this, because since we don't have points exactly on this line, we have to match some a little in front and a little behind. And if we're going to match it a little in front and a little behind, then that means we also have to do a reasonable job with this section and with this section in front and behind. So we really need to match all of them to do this. So the first thing is when we come into fit model, as I said before, we don't need all these points. So we'll start by just pressing shift and trying to select only points in this area. And I'm doing this multiple times because of the in and out of the plane, which right now is the Y direction. Points that are occluded won't get selected the first time. And so I'm doing this a few times just to give them adequate chance. And so this is sort of my first cut at the points I want to match. And so right now what I actually want to do is just get rid of the unselected points, right? I don't want to deal with those. And so now I'm dealing with many fewer points. Oh, notice over on the other side we were not occluded. So let's show all again, and let's hide. Let's no show our geom. Let's go back to our left view, and let's do this a couple more times just to make sure that we're getting anything that was occluded by the body. Okay, so now we should have all of those points. Come back in here, hide the unselected. So now we've got all the way around, we've got those points, and we can show this back again. And maybe I got too many. Maybe I should have trimmed this last inch. So what we can do now is we can say select none. And what I want to do is come in here, and now I'm going to select sort of the ones that are off the end and off the end over here, because I changed my mind. I don't want them. So I'm going to just select them, and now I'm going to hide the selection. And so now all I have is points that are sort of around the barrel section that I'm varying. And I want to associate them with the stack, and I want it to be free. So I'm going to add to target. And, I need to select all, and then add to target. And there's going to be a lot. There's that was 1,200 points, and since they all have UV coordinates that are free, that creates a heck of a lot of points to try and match. And the next thing that I'm going to do is I'm going to pick which things I'm going to vary. And so here we need to come into the stack. I'm at this 0th cross section. For starters, I'm just going to do it as 3 circles. So we're going to do it as a circle, and a circle. Oh, this one's an ellipse. We'll make it a circle. So here we're just trying to match 3 circles. We'll give it the freedom to change the Y and Z location of the first one, and so that'll be the overall. We'll give it the Y, Z relative location of the second one, and the Y, Z location of the last one. And so using that, I'm going to hit fit, and we'll see how it does. This may take a little bit of time. What I will say, optimization problems in fit model, this is way more points than I would normally use. I would normally never use 1,200 points. It's really excessive. I'm just doing it because it's quicker to select them and add them than it is to try and pare it down. You don't need a super detailed laser scan with a gigabyte of points to do a fit. You really just need a few points in the right locations, and fewer is better in a lot of ways. The way the algorithm scales, it does get more computationally expensive with more points, but what's more important is how well posed your optimization problem is, i.e., does your optimization problem blow up, or is there a very flat optimum where it can't find an answer, or do you have two of the variables that can be used to accomplish nearly the same effect? So in any of those situations, you'll have an optimization problem that's poorly formed, and the optimizer will have a really long time. It'll take forever to converge. This one should be well posed, but I suspect I just had way too many target points associated, and it's not going to work. I probably should have done it with many fewer as a starting point. So I'm probably not going to let this continue. But in general, hopefully this is the kind of idea of how you go about something when you're dealing with the middle of a shape, that if you want to match a single section. In general, I wouldn't ever match just a middle cross section like this. If I'm doing something like a body, I'm always going to start with the nose, and I'm going to match the nose, and then I'm going to go to the tail, and I'm going to get the overall length and the tail right. And then I'm going to look for what's the maximum cross-sectional area, and I'm going to match a section to that maximum cross-sectional area, and I'm going to move one little bit at a time. And that kind of one bit at a time process is how you should use Fit Model, and it's really just a tool to match the way you would do it with the eyeball these squares. If you were just, looking with your eye and moving the slider back and forth, saying, "Oh, that looks about right," Fit Model is just a way of doing that a little bit more rigorously. So this is probably going to crash here, or I'm going to kill it. But hopefully that helps to answer that question.
Thanks for going into that a bit more detail, Rob. And, for everyone listening online, we really appreciate you guys sticking with us and watching the videos. We hope everybody not only was able to hear and see everything well, but got a lot out of the talks. I think for the social Q&A on Conferences.io on the NASA Ames site, that link is still up and it should be live for the duration of the workshop. So if you think of questions or things that you want to ask after the event here is closed in a few minutes, you should be able to just go to that page and drop in a comment or a question. If there was something that wasn't quite working for you, by all means let us know. We'll try and see if we can make it better. If anybody has an additional question, feel free to type it in real quick. But otherwise, we've had a great set of questions and talks today. So really looking forward to everybody pitching in tomorrow. Again, go to the workshop main page and find the links to those sessions. And as you're following along, if you want the link to the next session for the afternoon, you can click Show More underneath your player, and it has all of the links and the schedule for each individual session. So thank you, everybody, for tuning in. That's really all I have to say for the rest of today. Rob, anything to add?
Nope. Thank you, everyone, for joining us. I'll see you tomorrow.
Yeah. So everybody have a good evening, and we will see you in the morning. Thanks a lot.